titled Organic Synthesis Towards Greener Horizons and Challenges and Scope. As we know, this GIAN workshop is a 5 days program. So today we entered into the 4th day of GIAN workshop. Thank you all for coming and joining with us here today. And from first day onwards, so delegates are coming and joining with us. And the very first day, Professor Beifuss and Professor K.R. Professor from IIC Bangalore, they joined with us. And later on, and the next third day, Professor Adimurthy sir from CSIR Central Salt and Marine Research Chemical Institute, he joined with us. Thank you very much, sir, for your kind presence. And for today, I would like to introduce Mr. Sagnik Ghosh, who is from LABINDIA Instruments, Kolkata. Please welcome, sir, with a big round of claps. Welcome, sir, for GIAN course. And I would like to draw your attention for today's program. So today we have 2 lectures and 2 tutorials. And in the morning session, we have 1 lecture and 1 tutorial. In the afternoon session, we have another lecture and another tutorial. So we are going to start with our first session with Professor Beifuss sir. And the topic is 3-component reactions with an emphasis on Povarov reactions. Please welcome, sir.
Okay, thanks a lot for your kind introduction. And you hear me? Yeah, I think so. Right. What I'm going to talk today is our multi-component reactions, and there will be some focus on one of the very well-known multi-component reaction, which is the Povarov reaction. And just to give you some idea what I'm talking about, multi-component reactions are very well known. And here is a definition that I think holds true still today. It's a chemical reaction where 3 or more compounds react to form a single product. So 3 or more compounds means that we at least have to react 3 compounds, but nowadays also 4 component, 5 component, etc. Reactions are known. It's important, of course, that we form a single product. Usually we don't focus on receiving mixtures. And these sort of multi-component reactions, they are based on the concept of domino reactions. And the definition of a domino reaction is given here. This is a chemical process which involves 2 or more consecutive reactions in which subsequent reactions result as a consequence of the functionality that is formed by bond formation or fragmentation in the previous step. And so some people will say they only consider CC bond formation as important, but I think we can use this in a broader sense. This is a very popular concept in sustainable chemistry, because it has to do with waste reduction, with reduction of time and effort and so on. So we can discuss this later on, which impact multi-component reactions have on green chemistry or sustainable chemistry. So there are some selected general reviews on multi-component reaction. The first review that I can remember is the review of Gary Posner in 1986, and a couple of years my former boss, Professor Tietze, and me just wrote a review on multi-component reactions, or better to say on domino reactions, and the definition that I have presented to you stems from that paper. So later on there were many more reviews on multi-component reaction, for example the review of Hughes and Ramon, and there is a book on multi-component reaction which is given here. And nowadays, a couple of years ago, you can go to Science of Synthesis, and they have edited or published 2 volumes on multi-component reactions, and the editor was Thomas Müller from Düsseldorf University. So when this is available to you, this gives you some nice and broad overview on multi-component reactions. So just to remind you, and I think most of you will know some of the multi-component reaction. This is one of the famous multi-component reactions. This is the so-called Viginelli reactions. Here are the Viginelli products, the Viginelli compounds. And what you do is that you just react a 1,3-dicarbonyl compound like a beta-ketoester, for example, with an aldehyde and with some sort of urea derivative, maybe a urea derivative or maybe a urea derivative, and the Viginelli products are formed. The references that are given here are all the references are from this Science of Synthesis multi-component reaction volume 1. So this is a nice, and more references can be found there. Then there is an older reaction, then there is a newer reaction. It's a so-called Gewalt reaction, and this can be used for making up 2 amino thiophenes. And what you do here is that you have a carbonyl compound which has acidic positions here, and you react it with some sort of cyanoester in the presence of sulfur. So sulfur isn't given in yellow here, since yellow color is so difficult to recognize. Nevertheless, you see sulfur ends up here at the core of the thiophene skeleton. Then another very well-known multi-component reaction is the Hansch dihydropyridine synthesis, and I have already introduced the Hansch pyridine or dihydropyridine synthesis to you when I gave an example of the lactase initiated of the lactase catalyzed oxidation of 1,4-dihydropyridines to the corresponding pyridines, and I also gave an example on a one-pot reaction that allowed us to come up with to produce the pyridines. So what do we do here? We need two molecules of a 1,3-dicarbonyl, and this undergoes reaction with an aldehyde, and then usually we do run the reaction in the presence of ammonia. And here you can see the fate of all the atoms here. Finally, we produce here the 1,4-dihydropyridine. So let us come to, I would say, one of the most well-known multi-component reaction. This is the Mannik reaction. And what you need here is a carbonyl compound again, and it's necessary that it is enolizable. And this is reacted with a non-enolizable aldehyde or a ketone in the presence of a primary or secondary amine. And what you come up with is what we call the Mannik base. Here you see in black the bonds that have been formed during this process. So I like this reaction very much, and it has been used very often as a tool in natural product synthesis. And here is a very famous Mannik reaction given, and it's the synthesis of tropinone. And this synthesis goes back to Sir Robert Robinson in 1917, and it is an example of a so-called biomimetic process. So later on, Schöpf and his colleague Lehmann, they optimized the process, and they came up with reaction conditions that allow us to produce tropinone in a yield of around 83%, so very high yield can be obtained. And if you have a closer look at this famous Mannik reaction, then you will realize it is not just one Mannik reaction, it is a double Mannik reaction. And so what we have here methylamine as the amine component. We have here this succinic aldehyde as the aldehyde component. And what we have here is the acetylene dicarboxylic acid, and this is the enolizable carbonyl compound. And what you can see is that these molecules are bifunctionalized molecules, so we have a double Mannik reaction. At a pH of between 5 and 6, at room temperature, after 3 days, and liberation of water and 2 molecules of carbon dioxide, you end up with tropinone. And you know Dystrophinone is the skeleton of the tropa alkaloids, and it can be used, for example, for the synthesis of atropine. And if you think about other tropa alkaloids, you will remember that, for example, cocaine has also this tropane skeleton. Right. So this is a very famous and interesting reaction still today. Then we come to the Pasolini reaction, and the Pasolini reaction makes use of the reactivity of the isocyanide. You react here a carboxylic acid, a carbonyl compound, and an isocyanide, and you end up with an alpha acyl oxycarboxamide. And here you form also some new bonds in one go. And related to the Pasolini reaction, this is not related to the Pasolini reaction. I just put this in the alphabetical order. So first comes the Strecker reaction. This is the reaction between an aldehyde or a ketone, the primary or secondary amine, and HCN. And what we end up is an alpha amino nitride, and this CN functionality, this nitrile functionality can be hydrolyzed afterwards, and after hydrolysis you come up with the alpha amino carboxylic acid. So this is a very easy access to alpha amino carboxylic acids in the end. So now we come to the reaction that is related to the Pasolini reaction. This is the famous Ugi reaction, and you see here is an example of an Ugi reaction where 4 components are reacted together: a primary amine, a carbonyl compound, an isocyanide, and a carboxylic acid, and they make up here an alpha acyl amino carboxamide. So this is one of the most famous reactions in the field, and it has been used in many fields, in particular in the field of medicinal chemistry. Now, what I would like to focus on today is a 3-component reaction, and this is the so-called Povarov reaction. And the Povarov reaction is named after a Russian chemist. His name was Povarov, and it has been invented around 50 years ago. So what do you need for a Povarov reaction? You need an aromatic or a heteroaromatic primary and or secondary amine, something like this. Most simple case is aniline, of course. Then you need a carbonyl component that might be an aldehyde or a ketone, and you need some sort of an electron-rich diene. essential medicines, so obviously a very important molecule. Then we have here this nicainoprol, which shows anti-arrhythmic properties. Here a compound with anti-HIV properties. Here a compound that can be used to treat Alzheimer's disease. Here a compound with anti-malarial properties, and here a neuroprotectant 1, 2, 3, 4 tetrahydroquinoline. And if you have a look at all these compounds, and this is just a selection of a few compounds from a very great number of biological active tetrahydroquinolines, then I think it's clear these compounds are, the synthesis of these compounds is of utmost importance. Review on tetrahydroquinolines can be found in Chemical Review 2011, and this was published by Menendez and his co-workers. Right, let's come to the Povarov reaction in more detail. So there are in principle several approaches to perform a Povarov reaction, and one type is the so-called two-component reaction. And what you do is that you react a preformed 2-aza-butadiene. This is the preformed 2-aza-butadiene. So it's essentially nothing else but an imine or an iminium ion, so it depends on the substituents, on the conditions, and a dienophile. And the other type is the three-component reaction, and here the 2-aza-butadiene is formed in situ by reaction of the aniline or the amine compound with the aldehyde compound or with the carbonyl compound that also may be a ketone. So all these three components are mixed, and you end up with the formation of the 1, 2, 3, 4 tetrahydroquinoline. And as you can see, this three-component reactions allows the creation of 3 bonds in a single operation. So here the bonds shown in red are elaborated during the Povarov reaction. So with respect to the mechanism is still today under discussion. So there are some controversies, as you can, as always. So let us start with the imine, with the 2-aza-butadiene, which is shown here, and this is now reacted with the dienophile. So then there are mainly 2 reaction mechanisms that have been proposed, and the one reaction mechanism is the mechanism of an inverse electron demand Atza-Diels-Alder reaction. So this is a concerted process that is shown here. So the primary product is this. This is an intermediate, and this undergoes here shift of the hydrogen to the nitrogen, from the carbon to the nitrogen, and then the final Povarov product is formed. However, there is great evidence that many of the Povarov reactions proceed in 2 steps, proceed stepwise, and so the first step is essentially the reaction of the electron-rich alkene or alkyne with the imine, and so this is some type of Mannich process. During this reaction, a positive charge is established here, and then this intermediate can undergo an intramolecular Friedel-Crafts reaction. Again, we end up at this charged intermediate, and now as here the aromaticity of the system is re-established. So these are the main reaction mechanisms that are under discussion, and it seems that in most cases we deal with a stepwise process and not with a concerted process. Right, catalysts. So if you assume that this reaction is an inverse electron demand Atza-Diels-Alder reactions, then we know that they are controlled by the LUMO of the azadiene. that interacts with the HOMO of the dienophile. And here are the two aza-diene shown, and you can simply activate the aza-dienes by lowering the LUMO energy of the two aza-butadiene. How can you achieve this? Just by using a Bronsted acid or using a Lewis acid as activator, as catalyst. And so we have typical Bronsted acids that are used to activate, like trifluoroacetic acid, like the CF3 SO3H, the trifluorosulfonic acid, the HCl paratoluene sulfonic acid, PPA, the polyphosphoric acid, or the camphor sulfuric acids. And these are just a few. It's no problem to come up with 50 Bronsted acids. So you can invent here some new acids if you like. There are so many opportunities that you can take. But essentially, it's all the same. Usually you have the choice, and you just have to optimize, and you will find which of these acids will be most suitable in your case. Very often Lewis acids are used, and here's also only a small selection of Lewis acids that have been used. So I would say BF3 eserate is the most often used Lewis acids in Povarov reactions. But you also can use the LNO, the lantane triplet, the scandium triplet, the yttrium triplet, the ytterbium triplet, zinc chloride, bismuth chloride, indium chloride, iron chloride, zirconium tetrachloride, tin tetrachloride, and so on and so on. So it's up to you what you choose. And I will show you that there are even other catalysts that can be used. Here, for example, is a very interesting paper making use of cellulose sulfuric acid as a catalyst. So this can be prepared from cellulose. Cellulose undergoes sulfonation, and you have, so to say, a catalyst that is made up from a renewable material. So here's a typical example. You have aniline, you have here the dihydropyrane, you have here benzaldehyde. You do this in the presence of cellulose sulfonic acid. 0 centigrade, 2 hours, and you end up here with a mixture of two Povarov products. It's a mixture of trans and cis. What does this mean, trans and cis here? So here the stereochemistry at this bond is controlled by the Z stereochemistry of the dihydropyrane. So here is only the cis. Here's only cis available, but here the phenyl group can be up or down. So we have here two possibilities. If you run the reaction in acetonitrile, then you will end up with a 65 to 35 mixture of the two diastereoisomers. If, however, you run the reaction in water, then you will observe a reverse of the ratio of the two diastereomers. So cellulose sulfonic acid, yes, it can be synthesized from renewable resources. Obviously, it is inexpensive. This is also easily recoverable, and the authors claim that it is biodegradable. So I don't know whether it really is biodegradable, but this is their claim. And this has been published in ACS Combinatorial Science a couple of years ago. So very interesting catalyst that is used here. So then even more interesting is the use of iodine as a catalyst. So we have here iodine catalyzed 3-component Povarov reactions, and they have been used for the synthesis of these indolo 3,2-C quinolines, which are shown here. So you start with the naphthylamine and an aromatic aldehyde, and here you have the indole as the dienophile. You can run this reaction in the presence of only 5 mole % iodine. Solvent is toluene at room temperature. A couple of examples, more than 20 examples have been published. Yields are between 55 and 78%. And it is here assumed this iodine acts as a mild Lewis acid, so it activates the carbonyl compound during formation of the imine, and it's also believed that it activates here the corresponding 2-aza-butadiene itself. So mild Lewis acid, mild condition, that's a very interesting catalyst for highly reactive systems. And you realize this is here a highly reactive system, since you have here the indole as a dienophile. So even better, I would say, is that you can catalyze this Povarov, this three-component Povarov reaction with enzyme. You can catalyze it with alpha-chymotrypsine. And here is an example. Here we have the typical starting material, aniline. Here we have the dihydrofurane or the dihydropyrane. We have aromatic aldehyde. What we need is catalytic amounts of these BPC, which is the bovine pancreas alpha-chymotrypsine. Do the reaction in a mixture of acetonitrile and water at 38 centigrades. Reaction time somewhere between 12 and 108 hours. 9 examples have been provided. Yields between 66 and 83% yields. Diastereomeric ratio up to 8 to 92. When we deal with the dihydropyrane as starting material, and diastereomeric ratio up to 71 to 29 when we have a look at the reactions with the dihydrofurane. Right, probably here one cannot come up with more examples, but in my view, the authors, they wanted to show that chymotrypsine, alpha-chymotrypsine can be used, and that is really a considerable achievement, I would say. And again, this has been published here in Green Chemistry, so there was a good reason, obviously, for the editors to accept these papers. Now, I want to switch to solvents, and I want to introduce a Povarov reaction, or Povarov reactions that have been performed in polyethylene glycol polymers in PEX. And here is the setup. An aniline is reacted with an aromatic aldehyde, and here we have a styrene type of compound with an E configuration at the CC double bond, and you react it here with one equivalent of BF3 etherate. So this is a typical Lewis acid that has been used here, not in catalytic amounts, but just in equimolar amounts. And here this PEC 400 has been used as the solvent. Reaction has been performed at 70 centigrades, reaction time 4 to 14 hours. Only 6 examples yields somewhere between 40 and 80%. But as you can see, the stereochemistry of the CC double bond in the dienophile is retained. And here you get a trans relationships. So what is the advantage? So we have to say, or the authors recognize, that the yields are lower than with acetonitrile as solvent. However, their argument is PECs are inexpensive. Yes, they are inexpensive. They are stable towards acids and bases. They are thermostable, and they are easily recoverable. The reason is that these PECs are insoluble in isopropanol and also in diethyl ether. So it's easy to work up here. Then these PECs are biocompatible, and it is known that they are of low toxicity. And so this might be a very interesting replacement for traditional solvents. It has been published some years ago, but it seems that not many people have are engaged in this and the use of PECs in relation with the Povarov reaction. Right, you also can perform Povarov reactions in ionic liquids. This is also possible. You know, the advantage of ionic liquids is that their vapor pressure is extremely low, and this is why so many people were interested in using ionic liquids as liquids in organic transformations. And here is one example that we have published. Again, a very easy model reaction: aniline, benzaldehyde, and dihydropurane. Furane is reacted to give a mixture of the cis and the trans product, or the endo or exo product. And we have shown that the outcome of this reaction very much depends on the ionic liquid that you choose. Here you see the BMIM BF4. So this is the butyl methyl imidazolium tetraborofluorate. That is the most well-known ionic liquid. Has been introduced very early and has been used extensively in organic chemistry for organic transformations. We do the reaction here in 0.1 equivalents of this ionic liquids. We run the reactions under microwave conditions, 70 centigrades, 15 minutes, and 51% of this 84 to 16 mixture can be isolated. So we do not need any additional catalyst, just the ionic liquid is sufficient. Obviously it catalyzes the Povarov reaction. So when you also can run the reaction under slightly different conditions, 0.1, again we use 0.1 equivalent of the ionic liquids, 70 centigrades, 14 minutes. In the absence of microwaves, then you end up with 44%, and the ratio is very similar. So the yields are not really convincing, I have to say. And so we were looking for better solutions, and here is one solution that gives better results. So this is not an imidazolium salt or cation any longer. This is a guanidinium salt. And here you can see the typical guanidinium core structure. And if you perform the reaction now with 0.1 equivalents of this ionic liquid under microwave conditions, 70 centigrades, 40 minutes, then you end up with 86% chemical yield, and the two diastereomers are formed in a ratio of 79 to 21. You also can run the reaction under thermal conditions. Yields are even better, and the ratio of the two ionosymers is also better. So don't believe people who tell you microwave is the solution of everything. Sometimes it helps very much, but sometimes it's always advisable to run a control reaction. And it's also advisable to run a control reaction not under these typical thermal conditions, but it's also advisable to run this reaction in a sealed tube. And sometimes the results that you get out of these sealed tube experiments are very much the same than the results you get out of the microwave accelerated reaction. So this is what we learned from this. We published this a couple of years ago in Helvetica Chimica Acta. This sort of chemistry has also published by Yadav. I don't know whether he lives in India, but I think, I have no idea, but I think he is of Indian origin, yeah? Is this true? Okay. And the only difference, the difference in these two papers is that he used this ionic liquid shown here, as far as I can remember, and the big difference is that he showed that only one product, namely this, has been formed. So we repeated the reaction, and I'm pretty sure that you end up with mixtures of the two diastereomers. So that's an old story, so to say. Right. Now let us come to enantioselective three-component Povarov reactions. And obviously, that's very interesting to use chiral catalysts. And here is one interesting example here. You have here an aniline, a 2-hydroxy aniline. React this with an aldehyde, and you react it with cyclopentadiene as the dienophile. And this is reacted in the presence of 5 more % of this ligand, which is shown here. This is an N' and double prime dioxide. This is how the authors call these ligands. and scandium triflate in a 2-to-1 mixture. And when you apply these N' and prime dioxide scandium triflate complex as catalyst, then you end up with more or less enantiomerically pure Povarov product. So 28 examples were provided, yields between 60 and nearly quantitative yield, diastereomeric ratio from 90 to 10 to 99 to 1, and even better enantiomeric excess somewhere between 90 and greater than 99%. So that is very expressive. Of course, you have to synthesize, or to get rid of this, you have to synthesize these ligands in order to use it. There are other solutions. You also can use a chiral phosphoric acid as catalyst. And this is mainly the chemistry of Masson and Zhu, or Zhu and Masson. So there are two corresponding authors in many of these papers. And you can see this chemistry has been published in JACS, so obviously very important work. And they have shown that IN carbamates can be used as dienophiles using this catalytic system. So why are IN carbamates that important? So if you have a closer look at the biological active tetrahydroquinolines, then you will find that very often the amino substituted, the 4 amino substituted tetrahydroquinolines of this type show very interesting biological, very pronounced biological activities. And so this was a good reason to try out that whether IN carbamates can be used. So 10% of these catalysts are necessary. Dichloromethane can run the reaction at 0 or at minus 30 centigrades. 18 examples, these between 60 and nearly quantitative. Stereomeric ratio greater than 99 to 1, and the enantiomeric excess somewhere between 92 and greater than 99%. Very important figures, very nice approach to these 4 amino substituted 1, 2, 3, 4 tetrahydroquinolines. This is the structure of the chiral catalyst. You see here the chiral phosphoric acid. Here is the idea of the transition state that has been provided by the authors. So you see hydrogen bonding obviously seems to be very important, and hydrogen bonding is obviously provided by the action of this chiral phosphoric acid here. So the authors have also shown that their method can be employed for the synthesis of really interesting molecules. So they were able to synthesize this one. The name of this one is torquetrapib, and this was, I have to say, this was a very promising CETP inhibitor, so a cholesterol ether transfer protein inhibitor. Unfortunately, the compound did not make it to the market, so it was not. There was some problems in, I think, second clinical stage. But you can read this in the review that I have provided on 1, 2, 3, 4 tetrahydroquinone. Nevertheless, this compound can be prepared enantiomerically pure using the method provided by Masson and Zhu, or Zhu and Masson. So, of course, there are other people using slightly different phosphoric acids, and the group of Luo and Gong and their colleagues, they have also developed an interesting chiral phosphoric acid nearly at the same time that the French group has developed their catalyst. So this occur nearly at the same time. Aniline, aldehyde, and here two hydroxystyrene have been used as dienophiles. 10% of catalyst, toluene, in the presence of a molecular sieve at room temperature. Nearly 30 examples yields between 20 and 95% diastereomeric ratio, 4 to 1 to more than 99% to 1, and EE between 83 and 97%. So interesting to note that here a quaternary center has been established. So this reason is, of course, the R3 substituent here. And related work with 4-hydroxystyrenes, that means the OH group in this position, again comes from Masson and her colleagues and has been published in the same year in 2012. Right, obviously, great number. Obviously, it's possible to come up with an enantioselective Povarov reaction. So there is some new development. Don't know whether this will be as valuable as the standard Povarov reaction conditions. So you also now can do an oxidative Povarov reaction. And again, of course, here the story is CH activation. CH activation. And there are two modes. You can either produce the radical here. What is this? What is this? What's this sound here? It's not from outside. Okay, I see. So you either can produce this radical, and this radical can then react with an electron-poor dienophile. This is the intermediate, still a radical, and this radical then has to be transformed into the corresponding tetrahydroquinoline. It's also possible to oxidize the starting material to the corresponding iminium ion, and this iminium ion is then electron poor and can react with an electron-rich dienophile, and again you come and you end up with the corresponding tetrahydroquinoline. But I'm pretty sure that this sort of oxidative Povarov reaction, that they will enrich the scope of Povarov reactions quite dramatically. And now there are many people working in this field. Here are just some leading references, but it's very easy to find, I would say at the moment, some 10 to 20 more groups that are working very actively in the field, and yeah, that's very promising. Now let me come to another topic. I would call this topic embedded Povarov reactions. So it's just the combination of a Povarov reaction with another reaction. So it's nice to have this three-component reaction. Fine, everything is good. I've shown, demonstrated that works pretty well. But can we combine the Povarov reaction with another one? Maybe there's another reaction that follows the Povarov reaction, or maybe there is another reaction before the Povarov reaction. And the rest of these lectures, I just want to show you some examples. So there is the domino-Povarov aromatization reaction, or I better should say it is a domino-Povarov elimination reaction. So you have here some standard starting material. We have here an enol ether, we have here an aniline, and we have here an aldehyde function. You do the reaction in the presence of one equivalent of trifluoroacetic acid, dichloromethane, 0 centigrades. Within 5 minutes, you end up with this quinoline, with this fully aromatized quinoline. So how does this happen? In the first step, we observed, or it is proposed, that the reaction between the NH2 group of the aniline and the aldehyde carbonyl group just occur. This iminium ion is then an intermediate, and this iminium ion then does react with the enol ether in the sense of a Povarov reaction. And this would be then the Povarov product. However, under reaction conditions, elimination of methanol takes place and a CC double bond is formed. So this is a very nice example of a domino-Povarov aromatization process. A bit more complicated is the domino-Povarov 1,3 sigmatropic rearrangement. So the starting materials are a bit more complicated. and the reaction conditions are also a bit more complicated. Here you have these 2-amino-benzimidazole. This 2-amino-benzimidazole carries an NH2 group which can react with the CO double bond in order to form the imine here. This occurs in the presence of piperidine, toluene, microwaves 120 centigrades within 5 minutes. And then you add an alkyne, but this is now an electron-poor alkyne. So not electron-rich, but an electron-poor alkyne. And the reason for this is that here, this is the first case that I introduce a base-catalyzed Povarov reaction. And so in this base-catalyzed Povarov reaction mechanism is a bit more complicated and does involve the base, namely the piperidine. It allows us to use these electron-poor dienophils. So the primary, there shouldn't be a transition state here, there should be an intermediate, sorry for this. The primary product is here, is shown here, but this primary Povarov product obviously is not stable under reaction condition. It does undergo a 1,3 sigmatropic rearrangement. You see here the R4 substituents. It is now here in this position, and then it undergoes a 1,3 sigmatropic rearrangement, and it ends up in the position shown here. And at the same time, there is a migration of the CC double bond from here to here. So this is I would say a complex example. Don't know whether whether the scope of this reaction will be broad, but very interesting thing to do. Now, there is a domino Povarov-Friedel-Crafts reaction. And okay, this is again a 3-component reaction, but here we start with a preformed imine. And this preformed imine is reacted with 2 molecules of this sort of furane. And reaction is performed in the presence of 5 mole% of a catalyst. And 2 catalysts have been used, and both of them are gold catalysts. So gold trichloride and the one that is shown here. And what you end up with is obviously a Povarov reaction, but also the introduction of a second unit of the furane itself. Reaction mechanism, of course, is a bit more complicated. The idea is that the whole thing starts with a Povarov reaction, as shown here. The 2-azabutadiene does undergo the reaction with 1 molecule of the 2-methylfurane, and the reaction takes place at the double bond that does not carry the methyl group. Okay, this is the Povarov reaction. Now the aromatic system has to be restored, as shown here. This is a 1,3 hydrogen shift, and this does which does produce these, which does restore the aromatic system here. Now, gold obviously does come into play, and the role that gold plays is just to activate these enol ether here in the way shown here. You can write a positive charge here, and you can write then another structure which demonstrate that a nucleophilic attack can take at this position here, and just forming this bond. This is nothing else essentially but a Friedel-Crafts reaction, since this is an allylic cation that has been produced by the action of gold 3. Another reaction that might be interesting is the combination of the domino-Povarov reaction and the hydroamination for the synthesis of the so-called ulolidines. there are also some natural products having this core. And how does this go here? Here we have a bit more complicated aniline, also carrying here a triple bond. First, the Povarov reaction takes place, aniline, aldehyde, ene carbamate. Here we have the formation of the 1,2,3,4 tetrahydroquinoline, and then again gold does come into play. Again, we have here a gold catalyst, the mixture of a gold catalyst and a chiral phosphoric acid. So we take 15 mole percent of this chiral phosphoric acid, 10 mole percent of this gold compound, and it is supposed that the two compounds interact and form a new catalyst. Right. So essentially this means that the formation of the 1,2,3,4 tetrahydroquinoline is enantioselective. And now gold comes into play in the way that it interacts here with the triple bond, does activate the triple bond, and a intramolecular hydroamination takes place. So this CN bond is formed during hydroamination process. And the only thing that remains to do is to reduce these CC double bond, and this for this purpose a reduction agent is added. In the end, the ulolidines are formed in yield between 47 and 72%. Diastereomeric ratio somewhere between 8:2 and 99:1. Enantiomeric excess are very high, between 92 and 99%. 17 examples have been published so far. So very interesting, combining these chiral phosphoric acid with the gold compound. Now let us make things a bit easier. So far we have had a view on reactions where the Povarov reaction took place first, and was followed by some other process. So my co-worker Hans-Georg Imrich, he came up with another idea. So he asked himself, is it possible to replace the aniline with the nitro compound? Nitro compounds much less susceptible to oxidation, easy to handle, and so on. And so his idea was to start with the nitrobenzene, compound, to reduce it in situ into the corresponding aniline, and then react it with an aldehyde and a corresponding dienophile. And as you can see, that works. He used iron as a reductant, and he used a mixture of iron and citric acid, to be precise. The catalyst that was used to bring about the Povarov reaction was a montmorillonite, this montmorillonite K10. The reaction was performed in water at 40 centigrades and could be performed in 4 hours. So 19 examples were published, yields were up to 99%, and here you can see the two products, the endo product as well as the exo product, and the endo-exo ratio is up to 100:0. So that's a method that can be used very nicely, using water as a solvent and the nitrobenzene as the starting materials. So this is an intermolecular Povarov reaction. It's also possible to do this in an intramolecular version, and a paper dealing with this issue has been published last year. Now let us come to another piece of work. Now this is a domino iodination, Korn-Bloom oxidation, Povarov aromatization reaction. So a number of reactions take place in one pot here. We start with an aniline, we have again here a carbonyl compound, but now you should realize that we need a methyl group in the alpha position, and we have a dienophile. In the presence of 200 mole percent or 2 equivalent of iodine in DMSO at 80 centigrades, 42 to 90% of this fully aromatized quinoline are produced, and we should realize here that we have here a ketonic substituent in the 2 position. How does that occur? So the course of reaction is as follows. In the first step, the methyl group, the alpha methyl group, undergoes iodination to produce these alpha iodo-carbonyl compound. This alpha iodo-carbonyl compound then can be oxidized just by GMSO, just by the solvent. And this is what we call the Kornblum oxidation. So as a result of the Kornblum oxidation, a dicarbonyl compound is produced. So an aldehyde function has been established. And the aldehyde is more reactive than the keto function. That means the aldehyde function does now react with the aniline, with the NH2 group of the aniline, to produce the corresponding imine. Now the 2-asa-butadiene is established, and now this is just activated by HI, as shown here, and is now reactive enough to undergo a Povarov reaction with the styrene as a dienophile. The Povarov product is shown here. However, this is not the end of the story. Under these reaction conditions, aromatization takes place, and the quinoline is the final product. So this is a nice sequence of different reactions that are performed in one box. I would like to go on with in situ generation of substrates, and now I would like to present the in situ generation of beta-enamino esters, followed by a Povarov reaction. What does this mean? We have an aniline, we have here a methyl propionate, we have an aniline, and we have an aldehyde, a benzyl aldehyde, and we have a second molecule of the aniline. So essentially, this is a 4-component reaction. So what does happen? The aniline does react with the methyl propionate in ethanol room temperature overnight, and does form the beta-enamino ester. And as we know, this is electron rich and can be used as a dienophile. So then you add some paratoluene sulfonic acid, and you also add here the aldehyde. Then this aldehyde reacts with a second molecule of the aniline to form this CN double bond. This is nothing else but the 2-asa-butadiene. Now the two substrates can undergo a Povarov reaction, and the result is shown here. These are the products. Certain examples yield between 41 and 67%. Brings me to another example of a in situ generation of a dienophile. This is the domino cyclopropyl imine rearrangement, Povarov reaction. Here we react 2 equivalents of an aromatic amine of an aniline with 2 equivalents of these cyclopropyl carbaldehyde. In the present, so here the catalyst is ammonium bromide, solvent methanol. Reaction takes place at 100 centigrades within 14 hours. Yields 90% of this example here. In total 12 examples, yields between 42 and 91%. Exo-endo ratio is somewhere between 57 and 49%. So what does happen here? Obviously, we have only 2 different types of molecules. And it's important was this cyclopropyl carbaldehyde just undergo, which reaction this cyclopropyl carbaldehyde does undergo. So one molecule of this aldehyde does react with the aniline and does form this imine, this cyclopropyl imine. And this cyclopropyl imine can undergo a vinyl cyclopropane rearrangement. And what is the result here is the dihydropyrrole. And the dihydropyrrole is now our dienophile. Then this dienophile reacts with more cyclopropyl carbaldehyde and aniline and the second molecule of aniline to give the corresponding Povarov products. That means our cyclopropyl carbaldehyde, one of the molecules ends up here and the other molecule that ends up here. That's a very interesting story. However, you have to work with the cyclopropyl carbaldehydes and you depend on this type of rearrangement. So a reaction where probably the scope is much wider is the three-component Povarov reaction with two ketones. You react one molecule of the aniline with two molecules of a ketone in the presence of magnesium bromide as a Lewis acid, 0.5 equivalents of lithium carbonate, 60 to 90 centigrade reaction temperature, and within a reaction time between 1 and 19 hours you come up with this dihydroquinoline, and this is a tetra substituted one, and we can realize that obviously two molecules of the ketone have been introduced. And if we analyze this structure, then we realize one of the ketones ends up here and the other of the ketones ends up here. And here is a typical example. I would say this is the example with the highest yields. How does that take place? Right, it takes place in the sense that one of the molecules of the ketone does react with the aniline and does produce these magnesium activated imine, and the other magnesium is responsible for the formation of this magnesium enolate. And this magnesium enolate, of course, is somehow nothing else but the missing dienophile. So we can make use of make double use of this ketone. And what you also can do, you can also extend this sort of reactions. You can have a three-component Povarov reaction with two molecules of a pyruvate and also with two molecules of an alpha alkyl ketoesters. So the approach is the same. The pyruvate as well as the alpha alkyl substituted ketoesters, they both act as a carbonyl compound and they both can be transformed into corresponding dienophile. So this is also a very nice piece of chemistry. Here this is catalyzed by only 1% of indium triflate, and the reaction is run under an acetonitrile at 80 centigrades. Right, I think that it was what I wanted to present you in the context of the Povarov reaction. You see, I think I could demonstrate that the Povarov reaction is much more than that was known in 1963 when the Povarov reaction was invented. So many achievements have been made. Many Lewis acids, many branched acids have been tried out. Many solvents can be used, many reaction conditions. We can make the reaction enantioselective, and it is possible to embed, to combine the Povarov reaction with other types of organic transformations, and this of course widens the scope of this Povarov reaction quite dramatically. So thank you very much. If there are any questions, we can have now some questions. If not, then I'm happy to give.
Whether we can do this Povarov reaction using the cage molecules so that it will have the internal acid.
What can we do?
The cage molecules, which will be having the internal acid.
What sort of
Cage
the
molecules,
cage molecule?
using the supramolecular chemistry.
I don't know whether you can. I don't know whether the Povarov reaction has been performed in that way. I don't know whether the cages are large enough. I'm not sure. I'm not aware of a reaction of this type. Might be interesting, but I don't know.
And you have shown that we can use a Bronsted acid in Povarov reaction. So can we use phosphoric acid derivatives as a Bronsted acid?
Yeah, as I have shown, you can use these chiral phosphoric acids. They are phosphoric acids. And also you can use, if you do not want to make it selective, and then I have shown that PPA can be used, and PPA is a polyphosphoric acid, so that can be used.
And in the starting you have shown that natural product can be synthesized in the Povarov reactions, right? So is that simple that you can directly use the Povarov reaction, you will get such a big molecules?
No, I have not shown that the Povarov reaction can be used to synthesize all these molecules. I have shown that the molecules with a 1, 2, 3, 4 tetrahydroquinoline core are present in nature. But to come back to your question, it is true that some of the molecules that were shown on that slide have been synthesized by using the Povarov reaction. And in particular, much attention has been paid to the synthesis of the martinellic acid. And of course, it is not as easy as it looks on first glance. So there is a lot of chemistry, and many groups were involved in this sort of natural product synthesis. But I have demonstrated to you that at least these talky tree buff can be can be synthesized in an enantioselective manner. Yeah.
Sir, in Povarov reactions, mainly one simple aniline is used. But instead of using aniline, if you use one aminopyridine. But if you use one aminopyridine is used, the Povarov reaction will be undergoing Povarov or not.
So if I got it right, you want to ask whether the aniline can be replaced with the 2-aminopyridine, yeah? Is it this? Is this your question?
Yes.
Yeah? Yeah, it can be replaced with 2-aminopyridine. In one of the first slides I showed you that aromatic amines can be used, but also heteroaromatic amines can be used as substrates for the Povarov reactions. And if you want to have a look at this sort of chemistry, then you have to look for a British author. His name is Mellor, M-E-L-L-O-R, Mellor. And he has published, I would say many years ago, 20 years ago, a lot on using heteroaromatic amines in the Povarov reaction. Yeah?
So in the Povarov reaction, feeder carpentry, you have used gold chloride.
No, we haven't. No, this is a false impression. We haven't done this. We haven't done this. We have only done the work where I have chosen that we have done this. So most of the work that I have presented here has been done by other colleagues, and this is why I put the names of the colleagues.
Gold chloride is used. AuCl3 is used. AuCl3 in the mechanism of feeder Povarov reaction.
I didn't get it. Sorry. Please again. Which reaction are you talking about?
or mechanism of domino Povarov reaction.
Domino Povarov reaction.
You have used AuCl3 is used.
Ah, okay, yeah. Yeah, probably, okay, this is obviously this is what's this example of this domino Povarov, do you mean the hydroalumination or you mean the Friedel-Crafts?
Yeah, Friedel-Crafts.
You mean the Friedel-Crafts. Right, okay, so the gold 3 probably plays a dual role. It probably catalyzes the Povarov reaction, but the main purpose of this gold catalyst is the activation of the enol ether, of the cyclic enol ether. So it forms then a carbenium ion, an allylic cation that is reactive enough to react with the second molecule of the fluorine. Right? Okay, I can show it to you. What is this? What is this? Who is this? Yeah, you mean this, right? Okay. So we have here the Povarov reaction, and this is probably also catalyzed by gold 3, I suppose. But first we have the Povarov, the initial Povarov product. This initial Povarov product has to re-aromatize. So this is done by a 1,3 hydrogen shift. So from hydrogen just migrates from here, from this carbon atom to this nitrogen atom here. And then here these cyclic ether here does undergo activation by the gold catalyst. And this is shown here. So some sort of cation is produced, and this is written here in the way as a allylic cation. And this allylic cation is then reactive enough to undergo a Friedel-Crafts reaction. So this is here the electron-rich part, and this is here the electron-poor part, right?
So can we replace this gold with any other cheaper metal?
Can be what?
Can we replace this gold by any cheaper metal quite?
I don't know. If you have time enough to do things like this, do it. I'm pretty sure. I mean, we can have a bet, right? Okay, I'm pretty sure that you can do this. There's always another catalyst that can be used. Sure. Maybe even without a catalyst. I don't know. Maybe just heating it up. No, I'm pretty sure that I don't know this. I don't know this, but I mean, if you are willing to run 1,000 experiments, right? I'm pretty sure that you will find other conditions that are gold-free. Yeah, but you should think about whether it is worth to do so. First, you should find out what is the scope of this reaction, for example. You see here a very interesting molecule. This is a methylfurane, so you have to make sure that you block one side of the heteroaromatic system. So only this side of the system does react where we have no additional methylfurane. So, and if you think about in terms of diversity, look, this molecule is introduced 2 times. And then, of course, you should have a look at the products. What can you do with the products? I don't know what you can do with the products. Right? But that might be very interesting, yeah? Might be very interesting. And as you can see, I mean, yeah, sure. One can try this. But this holds true for all this what I have presented here. You can try this. I'm pretty sure that you can come up with 5 or 10 more chiral catalysts which can be used as chiral catalysts to catalyze Povarov reaction. Okay.
One more question from yesterday.
Okay, sir. Thank you very much, sir, for your valuable knowledge. And you can continue this discussion session after the tea break also. And now let's have a small tea break. And please come with your tea inside, and we have a small musical session. And let's have a fun. So now after the tea break, we will begin session with tutorial.
Makes no sense to try this. I don't think it makes sense.
One of the questions from audience regarding supramolecular chemistry. What was that? Something regarding supramolecular chemistry. Somebody asked, no? From Povarov reaction. Okay. So whether the Povarov reaction can be combined with supramolecular chemistry. So that is actually very much modern concept. So that can be linked to molecular marriage and divorce. Okay, so molecule also used to get married and divorced. So that I will show you how it happens. So, which one you want first? Frustrated Lewis pair or molecular marriage? Which one? Okay, let us start with the frustrated Lewis pairs. Okay.
Rabia?
So frustrated with pairs. So what do you mean by frustrated? Everybody knows what is frustration, huh? Everybody knows what is frustration. You know how to release it also. Yes or no? Yes. Otherwise you will be mad. So see, this concept has been used recently. I mean, not so recently, but maybe in last 4-5 years, very nicely. So that basically goes, or basically that is rely on green chemistry, complete green concept. So that is the motto of scientists, to actually avoid some hazardous reagents to perform some basic reactions which are actually valuable for any kind of transformation. So what we know basically, so we know two concepts are bond breaking and bond making. So your chemistry rely on bond breaking, either bond breaking or bond making. So we can think of, I think we cannot see. Think you cannot see, or you cannot see? You cannot see.
इसको आगे रखवा लो ना बोर्ड थोड़ा शिफ्ट करना
वो लाइट नहीं सकते
लाइट जला दो
লাইটে পিছনে
পিছনে পিছনে
So if we see these two types of molecules, we have a bond between heteroatom in first case, and in latter case we have bond between homo. So how do they get cleaved? What is their usual process to cleavage of the bond? If these two cleaves, how you can cleave them? Generally it happens radicals.
Positive minus, plus minus, maybe. Cation and ion.
Cation and anion. So this is the normal way. So you create generally one is cationic, another is anionic. But if you have a bond between homo, then how you get? Radical. So homolytic cleavage. And this is
heterolytic.
heterolytic. So now the question is whether we can cleave a bond between two same atom heterolytically. Can you think of a cleavage of a bond which is in between two homo atoms, the same atoms? Can you break them heterolytically? Is it possible? Is it possible? In case of bromine. What does it mean? We are not thinking about pi bonds. We are thinking about sigma bonds. Is possible? Yes. How come? What should be the ideal condition to get cation and anion rather than radical from a bond between two homo atoms?
If you polarize the bond, then
how can you polarize the bond?
by the interaction of the
Electronegative. Lewis acid.
Electronegativity is same.
Lewis acid.
Lewis acid. Lewis acid will, it has tendency to bond with both. Okay, we need some external different condition. Okay, so we will not go in that details. I mean, there are a lot of possibilities. We will talk about how the frustrated Lewis pair has been arised. Okay, the concept. So we all know if we have amine, that's very general amine. And if we think about, suppose any boron compound. So we know amine is Lewis. We can take this is basic, and this one is
Acid.
acidic, Lewis acidic. So what should be the ideal reaction?
Adduct formation.
Adduct formation. This is your adduct. Okay? So that means they both can react very nicely. But now if you just design them, suppose we design this base and Lewis acid in such a way that they cannot react, then what will happen? If you design or if you select the base and Lewis acid in such a way that they cannot react, then what should happen?
they will frustrated.
They will frustrate it. Then what they will do? So how can you design? I mean, what should be the ideal condition that they cannot react?
Bulky base.
Very good. Bulky base, and you have to. One has to be relatively bulky, another has to be really bulky, so that there is no scope to react with each other. Understand? So suppose you think we can take suppose phenyl. Suppose we can take many other things, or you can take the tertiary butyl, 3 tertiary butyl group, here, here, here. Doesn't matter. I'm just giving simple example, not. So, if you have okay, so you see their space is almost covered around the boron and here. You can take some other groups also. Okay, I don't know which is practically how much covered, but just I am giving examples. So if you now these two you have, they basically cannot react because of their steric properties. Now what they can do? They will try to see whether somebody is around so that they can react fast with them. Okay. Now let us go for the typical example of a molecule, hydrogen. Is it easy to cleave? Hydrogen is easy to cleave? Yes or no? Not easy to cleave. But if you have hydrogen here, that will be nicely cleaved by these two guys. So what it will do is, it should, if it cleaves, that will be homolytic. But these two fellows, one is having delta negative, another is delta positive. That will insist hydrogen to become delta positive, delta negative. And it will give a heterolytic cleavage. So what it will form then? So I'll just write R. Okay. So it gives this one. See, it was frustrated, somehow it has released frustration. Okay, but still frustrated. What they can do now? They obviously cannot able to carry. The positive negative charge is always frustrated than the neutral situation. So what it will do is, it will, if you have now ideal substrate, where your hydrogenation can happen. Like how do you do your alkene hydrogenation? You have expensive metal catalysts like rhodium, like all those Wilkinson catalysts and many catalysts, Lindlar and all those things we have. So in this case, you can nicely, selectively reduce your double bond or triple bond to the corresponding saturated compound. So basically this is green. Green or not?
Yes.
Obviously it's green.
No metal.
You can reduce double bond. You can reduce triple bond. You can reduce carbonyl compound. Okay. So that's the idea of frustrated Lewis pairs. Now let us think about what Professor Beifuss has just was very kind to discuss with you regarding Povarov reaction. He has shown that in one slide, if you remember, that nitro instead of aniline, they have used nitro compound. So he's one of my friend, Hans Georg Imrich. I know him very personally. So that time I think the frustrated Lewis pair concept was not that much evolved. So now maybe you can apply this concept. So what one can do is, we can take corresponding nitro compound, let us put this one, plus, so using this green concept, maybe we'll be able to do the Povarov reaction very efficiently. So I'm pretty sure that at the end aromatization will not happen. So it will product will be very in pure form in the tetrahydroquinoline stage. So that is one of the advantages it can be. So, okay, this is the idea of frustrated Lewis pair. So we can do a lot of things using a green method. So what you can do is, maybe the other concept what I told, that also I can clarify now, and maybe in the next tutorial session, whatever questions you have, so one by one you can come here and you can discuss. And amongst yourself you can discuss. Is it okay? Still we have some time, so we can cover this. So now it is visible, I think, huh?
Right.
Everything is visible.
Yes.
So what is basic property? I mean, if you think about supramolecular chemistry, what does it mean by supramolecular chemistry? It is nothing but an interaction or weak interaction between.
Constant gauge molecule.
Yeah. So weak interaction between several assembly or several parts, and it creates an assembly, self-assembly. So that means if you suppose you think about your football, okay? You think your molecules are arranged just in a surface. You can think about it. No? If your molecules are if your molecules are arranged in a surface of this top surface, so definitely they will take some space also inside, because this molecules is not like this. So it has some other space covered, okay? So this side, suppose it will take some space. But in between some space will be free. It can be in many places, it can be free. And inside some place can be free. Okay? So there are a lot of empty space will be there. Now recently, I mean, it is already 2017. We are no more in the year of 1990 or 2000. So a lot of recent development people are thinking. So what we can do is, people have thought about. Most of the people tell, or many of people tell that supramolecular chemistry is maybe cannot be useful that much, but maybe there are some scopes if it can be properly utilized. Excuse me. Okay. So, what happens? We have space cavities inside. We have a space here, here, everywhere. So, we can think about one space is a door. Just think, this is a door, or any other channel. You can think about window. Okay, that means entry is also possible, exit is also possible, inlet, outlet, both are possible. Depending upon the properties inside, depending upon the properties, the chemical environment you define or you create, it will welcome through the door your n number of substrate that depend on how much space is available. Is it fine? That means they will come inside, so which is nothing but an encapsulation. Encapsulate. That means you just absorb it inside. Okay. Once they are inside, so depending upon their reactivity, that environment will make them react with each other. So that will be definitely selective, because it is not your conical flask or round bottom flask or seal tube reaction. The space is limited. Their orientation has to be in a specific direction. They cannot, their entropy is very less. Okay, it has to be oriented only in the specific direction or specific position. So depending upon the, so that is nothing but a driving force of regioselectivity. Your regioselectivity is only that, that the orientation has to be specific, or your reaction has to be in a specific position. That is nothing but a regioselectivity. So that will give you the product with specific configuration or conformation or something like that. Okay, so due to what I want to mean is, due to the limited space, entropy is less, and due to the different kind of orientations of the groups here, the orientation will not be defined by or not be selected by the substrate. It has to be guided by the internal environment. So accordingly they will align with each other. So after the reaction, since I mentioned already, the space is limited. That means it has to immediately kick off. It will just go out. It will just go out through window, your D plus E. Okay. So then you tell what is the use of this reaction. The use of the reaction is, suppose, think about a reaction . So, what is this molecule? Anthracene. Very good. So, if you have any diethyl. So what do you expect?
Diels-Alder reaction.
Diels-Alder reaction.
4 plus 2.
Huh?
4 plus 2.
4 plus 2. Where is the expected reaction? 9-10 position. These two positions are reactive. But using this concept, reaction does not happen here. Your reaction will be here. This is why it is nature paper. So, it's a very good concept. Nowadays it is coming up. I do not know how much it will catch the idea. We have also done something, but we are not really reproduce the result. When I was in ISC Bangalore, my 4 months I was just trying this one. So I couldn't able to reproduce the result. So one experiment gives this one, another experiment gives major, minor, it actually varies. So, but we have done some other reactions basically. So your Diels-Alder reaction will be here rather than here, that in the traditional condition. So molecular marriage, that means encapsulation, and through outlet, when it does not have any compromise, it goes out, divorce. Molecular marriage and divorce. Okay, so that's the concept. So I hope those kind of concepts should be really a green concept towards organic synthesis or in supramolecular chemistry. I think that will, in future, I hope that will cover some huge area. So any questions? Any questions? Everybody understood, eh? What is surprising?
In your previous idea, now regarding that perspective previous essay, so you have used hydrogen gas as an external agent.
Yeah.
So what are the conditions that we can use? That means any type of external agent we can use, or is there any condition in order to make the reaction successful?
Basically, so far you say, so far not really too much is done on this area. Basically, it is so far applicable only for hydrogenation reactions, suppose reactions. Okay. So far it has taken only the hydrogen balloon, and its reaction works in ambient temperature, room temperature. Okay, because you have also hydrogen, you should not use the higher temperature as well. And ether base, the ether solvent, and your 2 base. That's all the reaction conditions so far. There is no extra hazardous reaction conditions, only for hydrogenation reaction it is applicable so far. But people are, I think, working in this field very seriously, so something will come up. Okay. So the bond, which is basically easy to cleave, so you can polarize them nicely. Okay.
Sir,
Yeah.
how do you assign this equation as 9 and 10?
How I explain?
Assign.
How will you give me that question as
Which position? The middle position. Then you should see the IPSC nomenclature book. So you should know how to number, no? Organic molecule. Any other question? Okay, if you do not have any questions, you can discuss with me or Professor Beifuss later also. Just we can carry on for lunch. Yeah, so this is the ideal time. And so after lunch, we have one presentation from LABINDIA by Mr. Sagnik Ghosh. So regarding NMR, IR and microwave technique. Okay. So inorganic synthesis. Let's see. Thank you very much.
Kind attention, please. The session is going to start in next 5-10 minutes. Is there anyone outside? Please let them come inside. Okay. Okay then. We'll begin the session right now. So we have a lecture. So from Mr. Sagnik Ghosh. Sagnik Ghosh from LABINDIA Analytical. He has an experience of 15 years in the field of marketing. Right now he is going to give a lecture on usage of microwave in instrumentation for organic synthesis and confirmative studies. So please give him a big round of applause and welcome him. Sir, please.
Good afternoon, everybody. It's a very tough time after lunch, starting conduct a seminar, lecture, and to listen also is a very tough time. However, I will be thankful if you kindly concentrate on this part. I belong from LABINDIA. It's an Indian company which is doing business in this country for last more than 30 years. And we do have manufacturing units as well as we have some agency business also. We are exclusive channel partners for some products and we manufacture also. Here in my next slide, whatever you are seeing, these are all manufactured by us. Like we do have packeters, we do have cutting point, we do have page meter, we do have resolution test temperatures basically required for pharmaceutical and EPC, right? you have atomization spectrophotometers and individual spectrophotometer for metal analysis. Further, we are exclusive channel partner in India for microwave-based products like microwave synthesis. We do a microwave-based digestion systems also. We do a FTIR, which is required after synthesis for confirmatory studies. We do a benchtop NMR, again it is required for confirmatory studies after doing synthesis. And then we do have ICP from lab. This Bruker FTIR we represent Bruker Germany. This is from CE and USA based company. This is a unique kind of product, and during my next slide I will discuss only, I will concentrate on only this part of this micro synthesis part. As it was told that we represent CEM. CEM, you can say they are pioneer of microwave techniques. Not only microwave synthesis, they do have microwave dilations, microwave-based reaction systems, they do have microwave-based peptide synthesizer also. But for synthesis, this part remains same. This is the basic part. This model is called Discover. This is microwave accelerated chemistry solutions. This is accelerated. Why? With the energy of microwave, if you radiate microwave in your reactions, it will be accelerated at the same time. What you will get a faster reactions. In conventional synthesis system, the time it takes, but for microwave, it takes 1/4 of time, even less than that. Higher yields. In conventional synthesis or reaction systems, that percentage of yielding is not up to that extent what you get in microwave-based synthesis systems. Improved purity, your product purity will be improved compared to your conventional synthesis. What kind of reactions you can carry over? You can do pressurized reactions, you can do classical reactions, means open vessel synthesis that you can do. You can do stereoselective reactions, like if you need to go for sub-ambient temperatures up to -90 degrees Celsius, you can go with an attachment. Hydrogenation reactions, as Professor Malaka was saying about hydrogenation reaction with the balloon. Here it will not be balloon. In my next slide I will definitely describe on that. Nanosynthesis, material synthesis, and one thing I have not written over here, that hydrothermal synthesis also can be done. Hydrothermal synthesis means high temperature, high pressure, very high pressure. Now, these some unique features of that instrument. What I need to describe, it's a circular design as well as self-tuning design. Self-tuning design means, suppose for microwave, how many people of you are aware of microwave? Have you ever used microwave? Used? Did you face any difficulties in microwave? Everything is right. You didn't face any difficulties? Have you done any non-polar samples? How? With the same wattage? Because non-polar samples are not absorbed by microwave. Sorry, I told you reverse thing. Microwave will not be absorbed. Microwave will not be absorbed by non-polar samples. You need more wattage for non-polar samples. For polar samples, the reverse thing. If you radiate microwave in polar samples, your reaction time will be very, very much less because it increases temperature by anything. But for non-polar, you might have reached that polar and non-polar both and use solvent. Otherwise, system is compatible with traditional open vessel, as I told, atmospheric reaction, refractation, condensation, that can be done. When received, means you can use the same cap for your next synthesis also. It is not like that once you use that cap, you have to throw it out. You can use it, and you can use the same vessel also. Volume independent temperature monitoring. Volume independent in that sense. Suppose if you have some sample volume of 3 ml. Here what happens, I will go to the next slide. IR sensor is mounted at the bottom of the sample holder. That's why here you see the IR sensor here, it is mounted at the bottom of the side, not from the side. Because of that, independent of volume, it can sense your reaction temperature. Then change operating parameters on fly. Suppose if you are doing with your unknown samples, you are not aware about the absorbance capacity of your sample. For the sake, suppose you have applied for 50 watts and you are giving programming of 150 degrees Celsius within 3 minutes. But you have seen within 1 minute it has achieved 150 degrees Celsius. So there it is going to achieve, not achieve, it is going to achieve. But you need to give more time. Otherwise there may be chances for decomposition. In such case you can change the parameter of your reactions during the running time. That also can be done. Here as you were told, sir was saying about single mode or it's a focused microwave based system. It is not a microwave. I think most of you are familiar with microwave even in our household. What kind of microwave it is? Anybody have any idea? It is called multi-mode. It is not a single mode or a focused microwave system. Why? There your cavity is bigger. So microwave scatters in the cavity. So microwave density is also not uniform in the cavity. Here what happens? Here is the place where you place your reaction vessel. The microwave magnetron remains surrounds the your vessel and there is waveguide is there. The microwave directly reflects goes to your sample. That's why there is no scattering, and for that reason you will get a better yielding and better purity of result of your microwave. This kind of system is called focused microwave. Somebody used to call single mode microwave system. Here, as I told, that round button flask from 5 mm to 125 mm vessel that can be used for open vessel system. You can go for 10 ml vials where your reaction volume should be 7 ml, not more than 7 ml. Vial capacity is 10 ml. Here, then with the extra attachment, you can go up to 80 ml vials for scaling up. As it was told, you can reuse that snap, means wire cap, bend and receive. Why bend? It's kind of pressure cooker. Everybody is aware about pressure cooker. When you are cooking, after a certain pressure, it releases pressure, right? Otherwise, what will happen? Your vessel will burst, your pressure cooker will burst. There is a technique where the pressure after certain, you can set the pressure. After building up that certain pressure, you can release this pressure. That technology is there in this wire machine. This is called snap on turbulence cap. This cap. How to use it? It's very easy. Just snap it, then you can use it. The 10 mm wire looks like that. This is pressure atmometer, where you can monitor and you can control with this one pressure atmometer. These are reaction vessels. What happens? Suppose for that, this portion here, if your pressure develops beyond your set pressure, the pressure releases by this way automatically, and again it receives. After reducing that pressure, again it receives. So there, first of all, there will be no chances of, no chances, I should not say no chances. It happens sometimes in past also. If people doesn't have enough knowledge on microwave chemistry, before using microwave system, you must have some knowledge on microwave chemistry. What solvents can you observe more microwave and which will less virulent for nitrogen. One more thing, suppose you are running a reaction, you have some byproducts which you do not want. The user is aware that after building up this pressure, if I release that pressure, the byproduct will go, which is an unwanted byproduct. That way you can eliminate those unwanted byproducts with this technology, and number of times, how many number of times you need to release, that also can be defined to software. You can program it accordingly. This is actually called, whatever I described, this is called equivalent pressure management system. If your set pressure of 300 psi is the 300 psi is the limit, beyond that the wire can withstand, this is up to 400 psi it is tested. But after 300 psi or 20 bar, the system will automatically vent out the vapor or whatever it may be, so that the pressure can be reduced inside the wire. As I told you earlier, this volume independent pressure technology, the system has IR, this is IR sensor. Here it is IR sensor. When temperature develops, the IR sensor senses the temperature of your reaction. There, what happens? If your sensor is mounted in this way, it means you have to fill up your sample up to this much. Otherwise, temperature will not be sensed. But here, since it is mounted from the bottom, irrespective of volume, temperature will be sensed. This is hydrogenation. As Malaka sir was saying about hydrogenation, we do have accessories. This is called gas addition kit. With that gas addition kit, you can add up gases as per your requirement with the reaction. You can program those gases, flows, timings and all. That can be done through accessories. This is not the part of the basic instrument. But of course you can do it. Here what happens? In the reaction vial, where you are putting that reaction vial, surrounding that one spill cup will be there. Because of spill cup, if somebody, suppose he or she is not aware about the microwave absorbance capacity of the solvent, if it bursts even, things will remain in the spill cup. It will not go to the electronic part of the system. This is the precautionary measurement you can say that has been taken care. Here, as I told you about the spill cup, here is the reaction vial. Here it is spill cup. The cavity is this much. You can put spill cup first, then you can put your sample over here. In that way, you can do. As it was told by me earlier that on fly you can change your parameters, reaction parameters. Suppose you put 70 psi with a temperature of 100 degrees Celsius, which will reach in 2 minutes. Now you are saying the rate of increment of temperature as well as pressure is more, whatever you are expecting. On fly means when you are running your reaction, you can change those parameters. What you need to change, you can change the wattage. On what wattage the microwave should radiate. That also you can change. You can change the temperature. You can change the pressure. That can be done on fly. Means during the time of running of your reaction, you can change all these parameters over here. This is the thing. And one more thing which was not mentioned in this slide is cool mixture. It is minus 90 degrees Celsius you can go. You can do stereoselective reactions. You can do that reactions over and above. You can do temperature quenching reactions also. which is not mentioned over here, temperature quenching reactions means suppose your reactants need microwave. But at the same time, if you increase that microwave, there are chances, temperature will increase. If temperature increases, your product may decompose. There may be chances. So, to keep the temperature almost in lower side and to radiate microwave, so that you can get your product in that way, that is called temperature quenching reaction. That also can be done with the same system. Any questions?
Thank you, sir. Any questions? No? Thank you, sir. On behalf of department.
Yes, sir.
How in magnetism is basically similar in household this microwave setup and as well as in microwave reactors. So, what are the ways by which these two segments will differ as far as the safety is concerned?
Sir, safety means suppose in microtron and household microwave, you will not get any waveguides. You will not get any waveguide. Means your microwave is not guided by something. But here that mechanism is there. This microwave radiation will be guided in such way that it can directly hit your sample. Otherwise, if you see the magnetron frequency, household magnetron and this magnetron 2450. All these magnetrons say with same frequency.
Basically, so that means the frequency is same in both the cases. It's true. So if someone, suppose you have the magnetron also for the household setup. If someone wants to improvise it, someone is having a household microwave setup and wants to improvise so that to meet his own purpose, because many reaction or many type of material synthesis.
You want to mean the same magnetron to be used in the same instrument or what?
No. Maybe someone wants to improvise the setup itself by putting something else, not this one, suppose household one. Because this one we cannot break and open and all these things, so that can. So in those cases, what are the components, what are the things that one has to keep in mind?
What are the things?
Improviser to keep in mind.
First of all, sir, what are you thinking? To place your household magnetron to this instrument. You consider your household microwave as a microwave synthesizer. Whether your household microwave can control temperature precisely? No. Whether your household microwave can control the pressure of your reaction? No. It cannot do. It is microwave synthesis, doesn't mean only thing is microwave, sir. There are so many parameters are involved in between as I told that self-tuning. What is self-tuning, sir? Suppose you have programmed a reaction with 50 watt to reach up to 150 degrees Celsius within 3 minutes and to hold that 150 degrees Celsius for 5 minutes. Now, the thing is, you need to reach that temperature 150 degrees Celsius within 3 minutes. When you have started radiating microwave, the system is recognizing, understanding that 150 degrees Celsius temperature, it will reach not within 3 minutes, it will reach within 1.5 minutes. This is a unique technique is when used over here. Automatically the system microprocessor will recognize that, automatically it will give that feedback and it will start reducing the radiation of microwave so that it takes 3 minutes time to
reducing means it will decrease the wattage.
Decrease the wattage. That will be done by the system, not manually. Not manually.
It's a very pertinent question. Recently, one project came to us. We designed the software for that in C language. That is, what his answer is, as you told, a precision type of temperature controller along with a programmable timer.
And yes, of course, feedback is
that is 3 minutes on and then temperature is reached and then it is stable for another 10 minutes or so, something after that, the temperature gradient controller.
At the same time, you need to monitor the pressure also.
That is. So, one microcontroller along fitted with this, I think that will solve this problem. But the main crucial point is the temperature control of the magnetron. It is something very fishy. Fishy means it has a tendency to rise or shoot up very rapidly. So the gradient controller is required.
Until and unless they use microwave, they can't imagine how it rises.
So one microcontroller based PID controller, proportional integral derivative controller sort of hardware will solve this problem. So it's a very ingenious way he has asked that he can duplicate the instrument at his setup.
Sir, I have seen such kind of things in Stuttgar University, as I was saying, in chemistry department. They do have a microwave synthesis. While after I went over there, I found it is basically a conventional cooking microwave it is. They have changed the facial things of that microwave and they can't do closed vessel reactions. Only open vessel reactions can be done. That can be done in conventional cooking microwave also. Conventional cooking in market, how much it costs? High-end microwave, 6,000. Not more than that. They have charged 2 lakh, 2.5 lakhs for that. That is required, and these are all these IR sensors. All these things are NIST traceable things are there. That certificate will come along with person.
That is in the feedback part.
Yes.
And as you told, it's a very amazing thing. It is volume independent.
Yes, volume independent. That is very vital. Suppose your reaction volume is 2 ml, but if your IR sensor is mounted over here, 2 ml is here,
so it becomes volume independent.
How it will be changed?
But since it is at the bottom, it is volume independent.
Yes, volume independent.
But is it truly possible volume independence?
Yeah. Yes, yes. It's not volume independent.
Good.
Since it is and one more sensor is there. This is in situ sensor. Of course, one more sensor, temperature sensor. Because you are a man of electronics, sir. You know, IR sensor sensitivity is not up to that extent.
Right.
Right? If you need to do it in so precise way, one in situ sensor, temperature sensor also can be mounted.
Right. RTD type of platinum resistance thermometer sort of temperature sensor.
Wire kind of things
Wire.
from there.
Dual sensor.
Yes, dual sensors. That also can be done.
Actually, another thing, recently, not recently, probably about 5 or 6 years ago, one paper was published based on this change of this microwave setup itself. So what they did, a normal household microwave setup they have taken. They have seen their magnetron was focused from the top side. So the rear side of the microwave setup was free. So their objective was that microwave, if there is a hole in the back side of the microwave setup, household microwave setup, microwave oven basically. So objective was that they calculated something and they found that in that hole, if 8 centimeter long and 2 centimeter dia copper wire is fitted, then microwave radiation will not get out from this setup. It will remain within the enclosed environment. So their objective was that this whole box type of thing, whatever it is, backside there is a hole and in that hole there is a copper pipe fitted to that. Copper pipe, copper tube. Okay, copper tube, 8 centimeter long, 8 centimeter or higher, not less than that, and 2 centimeter dia. Through this, they have inserted the what is called glass tube to act as a condenser.
Okay.
And inside there is a reaction vessel. Reaction vessel means normal round bottom flask they used, and they have done the standard reflux type of thing reaction in that. And they compared this one with the commercial microwave, this Dode type, not this type, Dode type commercial microwave synthesizer. And their report was that in both the cases it is comparable. Electronics part they did on their own, means the way they control the microwave energy timing, they did it on their own. So that was the basics.
Sir, I don't believe so. Means science, what I am saying, as I told, that cavity is bigger, microwave will reflect. It will reflect here, 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 then it will go to your sample. There, the microwave density is not uniform. It cannot be. That's why, if you see in your cooking microwave also, there is a turntable. Why it is turntable? Because microwave uniformity is not same. That's why it turns here. In research gate microwave, also in big cavity one, this is called multi-mode microwave, you will find cavity, turntable moves this way 180 degree, then again 180 degree. Since uniformity is not same, you need to move your samples throughout the cavity so that it can take maximum output of microwave. Here in focus one, this is not required. Your cavity is smaller. Waveguide is there. That's why waveguide is there. That's why this slide.
This is not present in your conventional microwave.
No. See, your sample is straight over here. Magnetron is all around. Here it is magnetron, then microwave radiates from all around. Right? And it is directly, since due to waveguide, it directly hits to your sample.
But the circular portion is a waveguide.
No, sir, in between it is there. Circular portion,
Yeah, this is a waveguide.
circular portion is a
This is a waveguide. Reflection.
And it,
Reflection takes place.
and it directs your microwave to your sample here. In multi-mode system, you will not find such kind. Waveguide is there. In multi-mode also waveguide is there. But cavity is bigger now. That is the
major problem is the cavity size.
Yes. Cavity is bigger. That is the thing.
Now we understood. Really, very instructive.
That is the reason.
Very good way by the animation. That animation is very good.
Thank you.
Yeah. So can you do the reaction of non-polar substrate in the microwave?
You need to mix up with some polar samples also. Sir?
Without mixing the polar solvent, we cannot do that.
Mostly no. I need to take opinion from him. Sir? Sir, I'm asking, for non-polar samples, how you do in microwave?
Generally for non-polar solvents, for microwave, we need to add a drop of DNA, so generally that is preferred.
That is required.
If only 1 or 2 drops is sufficient. And it will not, generally it does not change the course of the reaction.
Okay, thank you. And one more thing for confirmatory studies, one of my colleagues is on the way from airport. I'm sorry, his flight got delayed. It was at 9:10 and it has started from Kolkata at 1:15 afternoon. So he has already reached to Imphal. He is on the way. Once he comes, he will give their presentation on benchtop NMR for confirmatory study of your synthesis result. Right?
Thank you, sir. Thank you very much.
In that part, okay, you are mentioning previous slide on that.
Which slide? This slide or next slide?
No.
Wild slide. Wild.
Wild. Yeah, this side?
Yeah. In this case, okay. We can separate byproduct, any type of byproduct or not? Is there any specific byproduct to be separate or not? I mean, all the byproduct can be separated by this instrument.
See, for that you must need to have knowledge about reaction and on what pressure it will be vented out. That also you need to know. If you are aware, then you can program it accordingly. But system is capable to do so. That's what I wanted to mention.
Thank you, sir.
Okay.
Thank you, sir. Thank you on behalf of Department of Chemistry. So now we have a tutorial. So Sir Mithun Roy will be taking care of that. Please wait for some time.
So, good afternoon everybody. So, it is now tutorial session. So, actually now you can remember, so last day I was discussing about the translation of green metals into the medicines. Okay, so can you remember all these things? No? Yes or no? Okay, so some of them you may not remember all the things, but at least few aspects you should remember. Okay, so I will be giving some of the case studies. Okay, so you have to come up with a solution and we can interact with people so that we can have some transfer of the knowledge. Okay, so I will giving you some case studies, you will just answer with me until we get the transfer of knowledge, it will be helpful for us. Okay, so first of all, now you can remember for so last day it was assignments also was there. I think hopefully all you have been done correctly. So let's say you have some platinum based drugs. Okay? So you have platinum based anti-cancer drugs. So what is the problem that is associated with the platinum based drug? Let's say, for example, start with cisplatin. Can you guess? What is the problem with the cisplatin?
Necrosis.
Yes?
Necrosis. Something.
Not exactly like that. Question is that
Platinum prevents in liver.
Huh?
Platinum prevents in liver.
No, platinum actually when it transported it is goes in the kidneys and stored in the kidneys. The kidneys cannot urinate with those things. Okay. So it stays in the kidneys and sometimes it goes to the brain. So you will have some problem associated with nephrotoxicity. Okay? And also you will have some nausea and all these things. Okay? So it is a problem. So actually what is the chemistry of this problem? You know, what is the chemistry? So what is happening there? Inside the cell there is a water. So this chloride gets replaced by the water and this rate of acquisition for the cisplatin, it is very very high. So what is happening here? So if this complex is formed, then it has a very high affinity to the thiols. Can I give an example of the thiol that is present in the cell? Cysteine, correct? Cysteine, it is correct. But there is an important, another important thiol is there that is controlling the redox mechanism in the cell. That is the glutathione. Okay? That is the glutathione. Okay? So what it is doing, the sulfur is coordinating to form okay. So this reaction happens before it goes to the nuclear DNA. Okay. So that you can, if you can remember the anti-cancer activity of this drug, so it is going to the nucleus and bind to the G7 position of the guanine, and then it inhibits the transcription process, and then finally cell cycle arrest in all the biochemical process it undergoes, and then it leads to a necrosis or apoptosis. Okay. So the thing is that because it is going to react with this thiol, before it reaches to the DNA in the cytoplasm itself, it is getting deactivated. So you need to have very high dose. And for chemotherapy, if you can remember, if you can, I think you have seen that one. Some of the people cannot survive with a 2, 3, after even 4 chemo dose. Okay. So there is a lot of toxicities involved with that. So since a lot of platinum is involved, and therefore it leads to a toxicity. Main toxicity is the nephrotoxicity. So the next question is that, how can you overcome this problem? Can you tell me? How can you overcome this problem? So that it is very good anti-cancer drug, but it has less nephrotoxicity. Can you tell me?
Using green metal, handium to zinc.
No, let's say in the discuss the platinum itself. Let's modify, give you some challenge. Let's modify platinum itself and you come up with a solution.
Maybe platinum 4.
There is a one example, platinum 4. Okay, platinum 4 is very inactive and it is inert in the cellular medium. Okay, but when it reaches to the cell, the glutathione itself, it reduces to platinum 2, and then itself will become a this is hexa-coordinated octahedral platinum 4 complex. Okay, so it is then reduced to again cisplatin. Okay, so you have advantage. You are inducing, you are giving a non-reactive platinum 4 prodrug, which is only react only after the reduction. Okay, then it is doing its tricks. Okay, then it goes and bind to the nuclear DNA, and then it is anti-cancer activity. It is showing anti-cancer activity. Okay, so this is very good example, platinum 4. Any other way? Is there any other way? Okay, the problem I told, it is associated here, this reaction, equation. It is very fast in case of cisplatin. If we can make it a very slow, then if we can make it a very slow, then it has sufficient time to reach to the nucleus DNA. So we have to give some time to reach the drug into the nucleus. Okay, let's make it a very slow. So how can you make it a slow? This equation, how can you make it a very slow reaction? Yes, yeah, you have to change the ligand. Okay, as I told yesterday itself, the metal is having some advantages. So if you can tune the metal with the appropriate ligand, you can change the activities of this molecule. Okay? So it is having very good advantage. Okay? So just you change the ligand. Instead of chloride, this is nothing but another class of drug. It is oxaliplatin. So people have shown that one. If we make this type of molecule, the rate of acquisition it is very slow. So it's getting enough time to reach into the nuclear DNA. Okay? So in this way you can do, and this is another strategy. Okay, platinum 4 product. Okay. Now you just please tell me what is the advantage of using platinum 4. Already is mentioned. So you can make it a more active drug, more active with a less side effect. Any other advantage that you can think of? To answer these questions, you have to look into this word, targeted. Okay? So this is the new challenge that you are given. How platinum 4 product you can make it a more targeted. Can you just tell me? Okay. Yes?
Painkiller might be as a ligand.
Benzo?
Painkiller might be as a ligand.
Benzo?
During the cancer, patient should have pain.
Okay, so this is one of the approach. Very good. This is different strategy. Okay, so this is not all, but we want to make it a targeted. So targeted means how can you devise a targeted one? Means you have to have some difference between the cancer cell and normal cell. Okay, and it is there. So if you let's say this is a cancer cell and this is the normal cell. Okay. So there is a difference in the microenvironments between normal cell and the cancer cells. What is the difference microenvironments? Let's say this is a nucleus and this is your all the things. This is a mitochondria. These are the nothing but a receptors. Okay, receptors. Okay, cancer tumors. The property of the tumor is that it grows very fast. Normal cell, let's say it takes around 24 hours to divide, and within 24 hours, and for this rate of division for cancer cell will be huge more. So you end up with the lumps of cells. Okay. That is tumor, uncontrolled cell growth. Okay? So they require more and more food. Okay? So one of the food ingredient is that platinum, iron 2 or iron 3. One of the ingredient. Okay? Then another ingredient is the folic acid. Folic acid. Okay. In addition to the iron, it requires the copper and other essential metallites. Okay. So, for folic acid in the cell, it is not so easy to incorporate anything. Cell has some efflux mechanism. Okay. Cell will not take anything. Okay. So you have to make your molecules so that cell can take all these things. Whatever you want, cell should take this one. Okay. So to And to recognize, there is a very good recognition for a molecule and your receptors. Without this recognition, the molecule, which is desired molecule, they cannot be internalized into the cells. Okay? So many of you, I think you have learned that endocytosis, exocytosis, that is a basic class elementary class 10 knowledge. Endocytosis means internalize the things into the cell by some process, okay? And exocytosis means getting out of the cells, okay? So let's say if this molecule is binding, then after some time it is this one, and then cell is covered, and along with this receptor, this molecule is inside the cells. Okay, so this mechanism in the cell. Okay, so endocytosis is there. So, like in the cell, there is a, let's say this is the folic acid receptor. This is expressed. That is a more quantity. It is a more quantity. Cell surface is having more quantity of folic acid receptors. Means it can take more and more folic acid. Okay, compared to the normal cells. Normal cells have, let's say, if it is having 10, it is having only 1. Okay, so now if we can introduce this folic acid into our desired molecule, that molecule is not easy to internalize in the cells, cancer cells, as well as it is not differentiating any cancer cells from normal cells. By introduction of this folic acid, it makes your target molecule more targeted. So it can target now through this folic acid. Okay, so for the folic acid receptor recognize this. Let's say this is a folic acid, so it could bind, and then through the endocytosis process, it go into the cell. Since its number is very less here, so more and more drug will reach to the cancer cell more, because here there is some targeting molecule. So we introduced one targeting molecule. Okay, so like platinum 4, if you want to make it a platinum 4. This molecule, these don't have any targeting specificity. These don't have any targeting targeting molecule. Just acetate. It cannot recognize the normal cell cancer cells. So if this molecule goes to the normal cell, where the glutathione is there, normal cell also will be killed. Okay. Let's make it a more targeted. So what will you do? Let's make a PEG linker, and then here you add, this is folic acid. Folic acid is having some acid group, so that can be coordinated here. Now this molecule can recognize the cancer cell. Okay, more in quantity compared to this one. So if it is going to the cancer cells, then it is reduced, liberate a cisplatin, and then do some activity. So in this way, the toxicity due to the non-specificity of the drug, it is reduced significantly. So in fact, if it is found out that this molecule, and they have not do not recognize the cells. This molecule recognize the cancer cells. And how to determine whether this compound is more toxic and it is less toxic? So there is a parameter, it is called IC50 value. What it is doing, so let we have 96 well plate where the cancer cells are grown in equal quantity. Okay, and then you just treat the drug, treat the cancer cells with your drug. with your molecule with a dose dependent manner. Then we will have something, if we increase the concentration, and this is a live cell. With the increase of concentration, you can see it is decreased. It can be decreased linearly, not linearly, but it decreases in some pattern. So if you do some non-regression analysis in that, so you end up with IC50 value. So more is the IC50 value means less toxic, okay, or vice versa, okay. So it is found out the normal cell, let's say GT3 is a one kind of cell lines, that is the normal cells, okay. Another cell line is it is there, MCF10A, MCF7. This is the breast cancer cell lines, and this is the cancer cell, and this is the normal cell. Now it is shown that if it is treated with this molecule and this molecule with this kind of cancer cells, this is also activated in MCF10 normal cell also. But this is found to be more active in case of MCF7. It is found that around 10-fold increase is there in the cytotoxicity with this targeted approach. So you are able to design a molecule that can target the cancer cells, and that is a very, very important aspect in the anti-cancer research. Okay, so now you have lot of cancer drugs. If you can Google it, you will find maybe more than 5,000, 6,000 cancer drugs are there. Most of them are FDA approved or it is in clinical trials, something like that. But none of the drugs, they cannot claim they are 100% specific to the cancer cells. This is the problem. So you have to make your molecule that 100% cancer cell specific. Then only that drug is the most effective. That time when the cancer will be finished, like polio is done. Okay, so this is the challenge. Okay, now you are telling some interesting aspect. Okay, so you can release this platinum 2. Now the thing is that cancer tumor cells are inflammatory site. Inflammation means there is a pain. So lot of hydrogen peroxide is released. And this hydrogen peroxide always, when it is generated, that is the pain, that is the signal that is giving to your brain. Okay, something, let's say your hand is broken, you have huge pain. What is the origin of pain? What is the chemical signal of this pain? This is nothing but ROS. It is giving signal to the brain, okay, something has happened, you just take care of this one. Okay, so this is the chemical signal ROS. So any inflammatory site, there is a more quantity of ROS in terms of hydrogen peroxide. Okay, so it is a pain. So let's say, what is the common painkillers? Can you tell me? Just very popular in India. Ibuprofen. Then any others? Paracetamol, there is a weak painkiller. Very good. Excellent. And then aspirin. Very good. Aspirin is there. So we take it even frequently. Some pain, we take these things. Okay, to get relief. So these are something they quench the hydrogen peroxide. Okay. So now the tumor size is also inflammatory site. So if we can design something that can release the paracetamol or ibuprofen or aspirin in the tumor site, so your failure will be not there. So you are treating with a drug, single drug, and it is a dual action. It is treating the cancers as well as it is overcome the pain. Okay, so it is overcoming the pain. So like you can attach here aspirin. Okay, it is nothing but a methyl salicylate, right? What is that? Aspirin. What is the chemical composition? It is a derivative of salicylic acid. Okay, very simple one. So you can attach ibuprofen, salicylic acid, paracetamol, whatever is that, and you can selectively release into tumor site. Okay? Okay. Let's say I want to design something. Let's say this molecule is having acidity value, let's say 1 micromolar. This is a very, very less quantity required to show the anti-cancer activity. Now, I want to have it more toxic with less side effects. So what do you design? So if we can have a dual strategy, if we can incorporate another cancer drugs, let's say doxorubicin, or any other Taxol type of molecule, or any other molecule that is already FDA approved and it is doing anti-cancer activity, so you will have dual effect. Dual effect of this cisplatin and also of this anti-cancer drug. So it is now, it is platinum chemistry in anti-cancer research, it is has gone to that level. Okay. So can you please tell me, except platinum, what are the other metals that is used for anti-cancer therapy? Can be used? Gold. Very good. Oranofin, for example, oranofin, it is a drug, currently approved drug. It is available in the market. That is used for treatment of rheumatoid arthritis. Okay, but the people have used this one, and it has shown some anti-cancer activity. There are a lot of gold complexes, gold in heterocyclic carvings are there. So the gold complexes are very active in some of the enzymes, metalloenzymes or enzymes that is required for cancer cells to regulate their activities. They target. Okay. So in this way you can design a gold. Any other molecule? Any other molecule?
The transition metal element.
Transition metal elements. It is some different role here. It is there. Definitely it is there. Okay. Now tell me one thing. I give you one choice. Let's make anti-cancer drug out of platinum or gold. What will you choose? What do you prefer to choose? Gold. Excellent. Gold. Why not platinum? As I told, platinum, whatever is it, platinum 4, whatever you take, ultimately it kidney cannot bypass it. It has to be stored in that. Whatever less quantity it will be stored. But gold, is there any problem? Did you find anything gold related toxicological disorder? Okay, you are eating Chyawanprash, right? Right? Some of the people are eating Chyawanprash, some of the eating, some in the childhood we are giving some of the with silver spoon or the golden something like that. People wearing golden ornaments and all these things. Why it is important? They are from ancient time itself. People are using gold for different purposes, for medicinal purposes.
The ionization potential is very gold.
So actually, the gold complexes, they have various kind of activities. If it generates ROS, that means some oxidation redox reaction. So ionization potential or the reduction potential of the gold 3 or gold 1, it is become very, very important. Let's say if it is targeting some of the enzyme, some molecule, it is go and bind to the enzyme, and lot of cancer related biochemical pathways are there, and lot of enzymes are involved in that. Lot of biomolecules are involved. So we target one of them, then cycle is arrested, and then tumor cell itself undergoes apoptosis. Okay. So it can have various activity. So by blocking some enzyme activity, or it can generate ROS. So if it generates ROS, then reduction potential becomes very, very important. Okay. Okay. So this is fine. So you have preferred to choose the gold. Okay. Now, let's I'm telling you, I given one other example. Let's make use of copper. What will you choose? What do you prefer to choose? Copper. Why is so? It is more greener, more cheaper. It's very, very cheap. So if you can make a compound with a gold, that will be very, very expensive. If you can make it a copper, it is a very, very less expensive. So that is the target. So how can I make a copper-based complex? What is the property of the copper that can show some anti-cancer activities? Number one point is that copper 1 and copper 2 redox potential, if you can make any complex, that is very close to 0. So you can settle the redox property of this. It can oxidize, it can reduce it very frequently. You can do it with copper. Okay, one of the aspect. And this is the aspect is very, very important, that if you take any copper complexes, the IC50 value is very close to around 10, 8 to 10 micromole. They are active. Okay. Another important aspect is that I discussed yesterday also. If you make any copper complex, what is the absorption value, lambda max for this one? Can you expect?
600 to 800.
Around, let's say, close to 600 to 800 nanometer. So there is a one technique for treatment of cancer that is called photodynamic therapy, where you can use a light for targeting the tumor site. Okay, so drug is injected, drug is non-toxic. When you expose to the light, then it become active and generate some ROS, do some anti-cancer activity. Okay, so you need a light. Which type of light? Which type of light? Light of higher wavelength. Okay, so why it is important higher wavelength? It is because it penetrates deeper into the tumor tissue. If you use the low high energy light, they cannot penetrate into the deeper into the tumors. Okay, so that's what you need to have a compound that can absorb in the visible light region, say 600 to 800 nanometer. That is called PDT window. Most of the copper complexes having that one. So that's why it is very, very important to use copper to have anti-cancer drugs that can be excited, that can be activated by using non-toxic red light. Okay, so this is one of the aspects. So like in case of copper, in case of iron, in case of vanadium, most probably oxo-vanadium, most of the cases, they are actually very green metals, cheap metals, but you can make use of this kind of molecule for your anti-cancer activity more better if you can design it. But this field is not explored. I didn't find any of this transition metal that is even tested even to the guinea pig. So that field has to be explored. Okay, it has some promising aspects. Okay. So another strategy is that now University of Sydney, Professor Des Richardson, one scientist is there. So he is doing this type of chemistry, different type. He is introduced some chelating agent. Okay, some water soluble, cell permeable chelating agent, so that it can chelate iron out of your cell, cancer cells. So now the cancer cell is having deficiency of iron. Okay, and because of this deficiency, as I already told, if it is made deficient, living system will be killed. Okay, like cancer cell will also be killed. This is one of the strategy to introduce some chelating agent. Okay, like you can make a chelating agent of copper, you can make a chelating agent of iron, that is required. Okay, so these are different strategies. So far we have not most of them we didn't cover, but there is enough scope to discuss with you people. So it is like that. So now it is advanced to that level. So many things has to be explored. So you can think of how can you design a effective metal complex with the green metals. Okay. So actually we are doing that one. We are trying to explore. We have explored some of the iron chemistry that is showing some anti-cancer activity. Okay, in the light. And then now Zulal is also doing some copper-based chemistry. It is cytotoxicity is reduced significantly, and we just try to evaluate why it is become cytotoxic. What is the mechanism, and how the mechanism but it generate ROS. Okay, so we just try to investigate those things. So we are planning to do some in vivo applications also in some IIT Kanpur. So let's say maybe something will come out. Okay. So thank you for your kind patience for this tutorial session. If you have any other interactions you want to make, please feel free. Okay, so thank you very much. Okay, so I will be here only. Any other lecture is there?
Thank you, sir. Thank you for your little information regarding the cancer cell. So now we have a tea break. So we have tea and get inside, then we'll have a discussion. If you have any doubts regarding whatever we came across in the last 4 days, we can have a discussion. Thank you.
क्या चाहिए?
मेरे पास है।
नहीं खाने चंदो भी कितना बचा
So you bring your compound. So normal sample that is excitation. So LABINDIA. So you cannot you synthesize this in and then characterize something also for that for characterizing collaboration. So they didn't have ready solution. And all for so that is yeah, but also doing the analysis. This also in there. You deliver this crystal, you get the structure for the reconstruction. It's cheap. But they don't do it in the way that having this also
Currently, most of the them will be collaborating.
दिमाग खराब करेगा. Then I cleared my MSc. My first placement was GlaxoSmithKline, UK, and the first day, induction first day, and my supervisor came. Deepak, they used to say Deepak, not Deepak. So Deepak, this is NMR and you have to handle it. मैंने कभी पढ़ा ही नहीं NMR, and again, then that day I started reading about NMR. Still I was not interested in NMR, but I have to work, so I have to study. Then I came back to India after 1.5 years. I joined BASF as a research chemist. Again NMR. So NMR is everywhere. The more you run away from it, it will come back to you. And you can't, if you want to be scientist, chemist, anything in chemistry, you have to know it. Okay? So listen to me. You can't sleep today. And because your future managers, your future scientists, so definitely we will meet someday. I'll be telling you about this and you will buy from our company. So let's start. So who has seen NMR machine? Yeah, here you saw it, right? Real machine I'm talking about. Okay, what it look like? It's like a rocket science, right? पहली बार देखा होगा तो ऐसे हो गया होगा, बाप रे क्या चीज़ है ये? Okay, कुछ नहीं है, बहुत complicated नहीं है, but इसके बहुत सारे ये maintenance और ये issues है. So I'll describe a NMR room, how it look like. A big NMR room having a separate isolated place, and in that a rocket-like instrument is kept, okay, with lot of connections, lot of drums around, and it will be protected area, and there will be one computer and one irritated operator. क्यों? क्योंकि बहुत सारा sample आता है पूरा दिन में, and she or he have to do all the time, and she's like, please go away. If you take sample, you take the sample to her and, madam, it is urgent, sir, it is urgent. No, go away. No, I don't have time. So that is also there, and sometimes if that person is very close to you, he will allow you to go to near the machine to put the sample, and that is a big achievement. Putting a sample in traditional NMR system is also a big achievement. When I did it for first time, I was thinking like I have become scientist. So yeah. So this is not, it doesn't over here. Okay. Next thing is you have to undress yourself sometimes when you go near the instrument, right? Do you know? You don't know. Achha, anyone can tell me what does it contain? Is it just electric system, right? A circuit, right? Circuit. I am not your professor. Don't get scared to me, okay? It have a superconducting magnet, okay? And magnet attracts the metallic stuff. So when you have a watch or anything in your coins or anything which is paramagnetic, which will get attracted to the magnet, so you are in danger. Some people have pacemakers, some people have steel joint. I can't go. Okay. So you have a lot of you have to be very careful when using traditional NMR. Okay. So what I'm going to tell you about why I'm talking so much about a traditional NMR. Now have you understood what is traditional NMR? This is how it look like. Okay. It have a superconducting magnet which is stabilized. Of course, anything in chemistry is related to stability. इतना सब reactions होता है, इतना सब कुछ chemistry में है. ये word हटा देंगे, stability. We are of no use. Okay. When certain chemical is like, suppose acetone or aldehyde or ketone, anything. When it is reacted with B something, suppose B something, then why it go under reaction? Why it undergo reaction? Because it won't become more stable. Okay, so this is how it comes with the analytical chemistry. Analytical chemistry, of course, it is the instrumentation part. but it also need to have. It's okay. It's okay. Thank you. So again, the instruments also need to have stability, and NMR have a superconducting, traditional NMR I'm talking about. It have a superconducting magnet which is stabilized with the nitrogen or helium at the low temperature. Okay, so I think you are clear with the instrumentation part of traditional NMR. अब समझा कुछ ये थोड़ा idea? Next we will see. Now अभी सब बोलेंगे कि हमारे पास FTIR है, मास है, हमारा केमिस्ट्री ऐसे ही होता है. Why you are telling us NMR आके क्या बोल रहे? तो I'll tell you why NMR is important. Have you done FTIR? FTIR gives you functional group identification, okay, and it doesn't give you 100% confirmation. Am I right, sir? Yeah. And mass spectroscopy, everyone knows. Okay, so mass spectroscopy, of course, you get a mass, molecular weight of the substance. But if there is an isomer, how you will find that this is the molecule? So again, we are in a dilemma of the analysis. Then comes the NMR. NMR gives you confirmation of final structure. It gives a peak. It gives peaks for certain atom. Okay, and it gives us a peak, yani matlab overall spectra. Okay, okay. So NMR is very important for organic chemistry, for synthesis, for synthetic chemistry, for anything related to organic chemistry. Okay. Then what NMR need to have, like what NMR have, what are the different kind of steps? So we'll see there are proton spectroscopy, one-dimensional spectroscopy. So what if your instrument can only give one-dimensional spectroscopy, means what? You are again in 10% loss of confirmation of structure. So you need to have two-dimensional spectroscopy. That is very important. Okay. Then you have proton. Proton, अगर मैंने एक system लिया जिसमें proton 1D है. 1D means one-dimensional. Then I am again losing something. I am not getting proper results because proton 1D will give only 90% confirmation of the molecule. Whereas two-dimensional spectroscopy will give you 100% confirmation. Thank you. Then comes the carbon and carbon two-dimensional spectroscopy. It is again the same way. Suppose you have to submit a molecule to a pharmaceutical company or any customer or anywhere. Like suppose you have to show to your professor, for example, you have made a molecule in lab and you feel it is the same molecule what you desired for, but professor won't believe your instinct that you have made. He wants results. So how you will show him the results? You will first of all take NMR. If NMR is giving you proper peaks for that molecule, then only you will go for further mass, HPLC and other things. So NMR is important. Again, in proton, your professor might ask 2D का है. So पहला चीज वही पूछेंगे, scientist हो कोई भी हो 2D पहला पूछेंगे because it gives a confirmation of the structure bonding between hydrogen and carbon. Okay. Next, how to select an instrument? NMR. Suppose tomorrow you become a general manager of some company and your management says, come on, buy an NMR instrument. Then ऐसे ही थोड़ी जाके shopping mall में ले लेंगे, नहीं? कुछ पता होना चाहिए उसके बारे में, क्या चाहिए हमें, what is needed in that. So 4 factors are very important. First of all, resolution. Resolution जितना कम रहेगा उतना sharp peaks आएगा. Means if resolution is less, you will get very sharp peaks. So have you seen this IR spectra? ऐसा पहाड़ जैसा आता है, right? अगर तुम्हारा molecule, तुम्हारा sample is not proper, your KBR palette is not good, you have not done a good simple preparation. So you will get a lot of hums and you are not able to. Very clear spectra also is unrecognizable, but in NMR, it's peaks. Peaks are very important. If that instrument take a sample analysis more than 20 minutes, 30 minutes, then it is not useful, right? So your sensitivity is proportional to time. तुम्हारा sensitive जितना ज़्यादा होगा उतना, sorry, inversely proportional, उतना कम time लेगा, right? So it should be very sensitive. Then is a consumable cost. Up, you bought a machine, okay? You bought a machine, but you are not having funds. You don't have money for maintaining that instrument. So that is very important. Nowadays, everyone is looking for maintenance-free instrument. Okay. So here you need to see at the post-buying cost. Okay. Consumable cost, like आपका कितना accessories लग रहा है, what are the sample tubes, and lot of things. When as we go further, you will come to know what is the consumable cost. And the fourth thing is upgradability. Suppose today you had a project in which just proton was needed, just proton spectroscopy was needed. But tomorrow you got a project where you need to have carbon also. So you can upgrade the instrument or not. You have to look at that. So your instrument should have these 4 parameters, very important prime factor to look at. Okay, let's go further. Now, so I told you NMR का वो बड़ा instrument, उसमें nitrogen or helium you have to fill every week, 3-4 days, depends upon the usage of the machine. So it will you accordingly. So you know helium and nitrogen also cost. It doesn't. We don't get it for free. So it is again a post-consumable cost. So what is so special about this instrument, which I'm going to talk about today, is a Magritech. Magritech is a New Zealand-based company who understood the pain of the chemist, scientist, every organic synthetic chemist, what they are facing because of NMR instrument. So they designed and manufactured one benchtop NMR called SpinSol. The name of the brand name is SpinSol, company name Magritech, New Zealand. Okay, and I'll tell you some key words for this instrument. और मैं वो छोड़ दूंगा आप लोगों को. आप लोग के दिमाग में questions चलेंगे. What is Deepak is going to talk? So benchtop मतलब bench के ऊपर कोई instrument bench के ऊपर. Then cryogen free. Cryogen means helium, nitrogen. Free means you will not require cryogens here. Then comes the online reaction monitoring. This is, I'm not going to explain anything, will come later. Robust, it is very, itna fragile nahi hai. It is very strong enough to take the different kind of uses. Then fast analysis, the least time taken for analysis is 10 seconds. Now I'll tell you some unique features where you will understand why this machine is so nice. Permanent magnet technology. I'll tell you, in traditional NMR you have big magnet, okay, and which is suspended and which is stabilized by cryogens. But this is a permanent magnet which is designed by Aachen University. It's a patented technology and the design name is Halbeck design. You can Google it at home, Halbeck design. There's a different kind of arrangement of the magnet which gives a uniform magnetic field. Okay, so magnetic field जब बोलता हूँ तो NMR instrument में सबसे important है. वो नहीं रहा तो कुछ नहीं होगा. So that is very important, magnetic field. And your magnetic field, if uniform, then you will get a good results, good analysis spectra. Okay, so permanent magnet technology, again keywords I'll tell you. Halbeck design, patented technology from Aachen University, Germany. Next, cryogen free. I already told you it's cryogen free. No consumable cost, of course. If you don't have to buy nitrogen, helium, anything for your instrument, means your post consumable cost is 0. Okay. Then I was talking about you have to undress yourself before entering into NMR room. You have to take off everything like your watch, all metallic kada. Girls faces more problem and coins and everything. So you don't have to worry about here because the stray magnetic field is instrument. So you can, like this is an instrument, I can stand next to it very easily, without any problem, without any worry. Then comes what all analysis it gives. It gives one-dimensional spectroscopy and two-dimensional spectroscopy, which include proton, carbon 13, fluorine 19, including COSY, JRES for coupling constant, okay? Head core, depth, HMQC, HMBC, HSQC. This all are possible. किया है कभी तुम लोग ने कभी स्टडी तो किया होगा टू डायमेंशनल स्पेक्ट्रोस्कोपी everyone is blank what he's talking about yes today you have to google it because I will be in your dreams talking about COSY or something so you better study today at home. Then comes non-deuterated solvent. Now this is again for spectroscopy, NMR spectroscopy, you need to have deuterated solvent. Here you can use non-deuterated solvent for analysis also. Air compress free, अब ये कहाँ से आ गया? जो traditional NMR होता है उसमें NMR tube spin होता है, ठीक है? उसके कारण results आते हैं, वो उसका stability और spinning के कारण वो सब एक system बनता है. But because of uniform magnetic field, because of high stability, it does not require compressor. Compressor is used for spinning and all. Okay? Then easy of use of operation. It is the software is very easy. If I'll tell you, if I teach you for 1 hour, tomorrow onwards or the next moment, you will start using it very easily. So it is nothing a rocket science. With spin solver, you can do NMR anytime, anywhere. Then online reaction monitoring. Again, I'll leave this here. Let me, put something in you. अभी तुम लोग तो of course scientist हो तो you must be thinking क्या बोल रहा है online reaction monitoring. So it is very important you keep thinking, and I'll come to that point later. Now specification, of course. Now we need to see what are the specification. जब हम लोग when we buy phones, we of course look at the Android version. 5.5 है, 6.1 है, RAM कितना है, सब everything we look at, right? So of course scientists look for this specification, and tomorrow you will also look at these things. So frequency 42.5 megahertz. 50% resolution, very important, I have already told you. 50% line width is less than 0.5 hertz. It's a documented 0.5 hertz. But my system in Mumbai gives 0.34 resolution. So I told you, lesser the number, higher the sharp peaks. More you will get the sharp peaks. So resolution is inversely proportional to sharpness, right? Then comes sensitivity. अब sensitivity measure कैसे करते हैं? 1% ethyl benzene with single scan, how much it gives? So it gives greater than 100:1. Okay, greater than 100:1. Very important part, sensitivity. You have to look for an instrument, and it is very high in the market, which gives you a very fast results because of its high sensitivity. Okay. Next is, now again this point comes to consumable cost, post-consumable cost. You can't put directly molecule into the NMR instrument. You need to have an NMR tube. Okay, and NMR tubes with different instrument, with different benchtop NMR, they have their different. So if you buy an instrument, you have to always procure the NMR tubes from that same company. But this instrument does not require procurement from Agritech. It is commonly available, 5 mm OD into 7 inch length. This is very commonly available, you can get anywhere. And very, I will not say not expensive, it is not expensive. Then permanent and cryogen. This is this, if you look at the dimension, it is 1 unit, 55 kg. So you can imagine 1 unit 55 किलो का 55 किलो का एक इंस्ट्रूमेंट कितना दो लोग एक लोग भी अच्छे से उठा सकते हैं, ठीक है? Then because of fast automatic lock, you can use non-deuterated solvent. Okay, let's go further. This is some calculation for a resolution. You need to have a instrument frequency into 100 upon the resolution it gives at the time of shimming, and you will get the sensitivity. Let's go further. And this is how the sensitivity is calculated. Peak to peak noise upon 5, and this is, if you want, I'll send you later. And our instrument gives greater than 100. means sensitivity is 5 times better than other instrument like higher version. I'll tell you, अभी सब यही बोलेंगे बड़ा है, ज़्यादा मेगाहर्ट्ज रहेगा तो it will be very good, it will give very good results. But I'll tell you, bigger the magnet, more you will require to stabilize it. More power or more efforts you have to give it to for stabilization. And because it's a permanent magnet, compact, small, इसका stability का issues नहीं होती. Okay, let's go further. Now you can see some of the examples for two-dimensional spectroscopy. Some of the experiment. This molecule is ibuprofen. I hope you must have heard ibuprofen, right? Yeah. So this is cozy. You can see the details of the spectra, and you can see how clearly you can correlate between proton and proton correlation, right? This is JRES for calculating the coupling constant. Then hit core, again the same molecule I am showing you. This is head core, HMQC, HMBC. Depth is also important. You must be knowing depth is very important for if you are confused with the structure of a molecule. Depth is also necessary, and the spin sol gives you liberty with the different angles you can take. Depth at 90, 45 and 135 and together. So this all are possible on spin sol. Next is T1, T2 relaxation studies. This is for physical chemistry who work on nanoparticles, and they study the spin lattice structure and all other studies with the T1 and T2. Now comes online reaction monitoring. अब ये क्या आ गया फिर से? ऐसा हो रहा होगा नहीं? मालूम है सबको online reaction monitoring? Okay. So till today, everyone must have. आप लोग तो you have done a lot, but you must be doing lot of reactions. And how do you monitor a reaction? TLC, of course, we do TLC. And any other method you can monitor? NMR. How do you monitor it?
Take a sample and analyze.
Who is speaking? Okay, yeah. Yeah.
Take a bit of sample after some time, then look out for what are the intermediate.
But you know what? You are not able to get a proper result, because again you have to dilute your solution. You have to dilute your sample, and sometimes what happens? You need to have that instrument free for your reaction monitoring, right? NMR you can do, traditional NMR. But if I want every 10 minutes my sample to be analyzed, because my reaction takes around 20-30 minutes, like 1 hour. So how you will monitor? That is not possible on traditional system, because again you have to queue up, and that meanwhile your reactants have reacted. So this spin sol gives you freedom to monitor a reaction. So this is the NMR system. This is the NMR system, and this is like, have you heard of flow chemistry? It's very booming field of chemistry. Okay. So this is spin salt and 3 pipes, you can see 4. This is nothing a different kind of, it's not a building, it's pumps or the system where 4 reactants are kept and they are coming together in this rotating pipe. This is flow chemistry, जहाँ आपका चारों reactants circle में घूमते जाएगा वही react करेगा. That is different case. But if you are using in reaction vessel like 3 bottom, 4 bottom neck flask, so what you can do, you can just put this reaction next to the system. One inlet will go on the top of the. Can you see the top? There one. This thing is going on inside. Your Teflon tube will go inside, and it will come from this end, the bottom of this, and back to the reaction vessel. So, and this software allows you to perform the reaction monitoring according to you. Like you can customize it. Like 10 minutes, 5 seconds, any time, whatever you want, it will bring the sample, analyze, throw back into the reaction mixture. So it means you are not wasting your reaction mixture. Whereas when you put the deuterated solvent, you are losing your reaction mixture. For example, gold catalysis, you can't do reaction on gram levels. You have to be very, very bacha ki you have to. So that is very, very important. You have to be very careful when you perform very milligram reactions. So the spin salt gives you analysis. Like you can see here, this is the NMR, this is the, and if you want to do flow cell chemistry, then you need to have few accessories, parasitic pump and tubings, and which will allow you to perform and the analysis of the reaction mixture. See, you can see one of the examples. Fluorobenzaldehyde, aniline, TFA, going together, coming into that single pipe where they are rotating and they are reacting in that pipe. That is called flow chemistry. And they, after a certain time, they go to a spin salt, get analyzed, and later on come back to the mixture. This is how the software look like. You can start like manual 15 seconds to 1 hour. This is where the samples will be taken from the reaction mixture and sent for analysis. And you can also customize the scanning number of scans for the sample. And this online reaction, हम लोग सब scientists हैं. Somebody says something about science, we ask for proof, right? Are we? Yeah. So we ask for proofs. And how we prove our chemistry by means of publications, papers. And this is the chemical sciences paper. This is the journal which says online reaction monitoring on spin salt is very effective. It can be performed very well. Okay, so this is with the proof. This is not like Deepak is saying, so it will happen. This says, not me. Okay. Next is sensitivity and speed. If you look at the 4 spectra, this is a ibuprofen molecule, the same molecule with a different concentration, keeping constant amount of solvent. So 2 molar, 200 millimolar, 20 millimolar, and 2 millimolar. So these are the different concentration, and you can look at one scan, same then 1 scan and 40 scans. So you can see this. This one is 1 scan 7 seconds. So you analyzed one big ibuprofen molecule in 7 seconds. Okay. Next is this one. Again 20 milligram. 1 scan 7 seconds. As now you can see it's very diluted sample. So you need more time to analyze. Okay. So this is how the spin salt is very sensitive, very very quick in analyzing the samples. This is fluorine and proton NMR on one system. So we have 3 systems: spin salt proton, spin salt carbon, spin salt phosphorus. Now what 3 different model gives you? Spin sol proton gives you freedom of analysis of proton and fluorine. Carbon gives you proton, carbon, fluorine. And phosphorus version gives you proton, phosphorus and fluorine. So proton and fluorine is complementary to all them. Okay? So let's go further. If you look at the fluorine sample, and it gives a very good sharp peaks. These are really performed. This is not just a picture. These are performed on the spin sol instrument. Let's go further. This is the this is the software look like. And now very important part. If you have seen NMR, you have to shim it. Shim it means calibrate it before each experiment. So in traditional NMR, matlab, suppose I have done analysis now, then again I have to shim, then again I have to shim every time. But here in spin sol, you have to shim it once a 24 hours. Means aaj shim kiya to parso karo. You don't have to shim it every time. This saves a lot of time. And you have to shim it with 10% D2O. D2O 10% with standard tube रहेगा, उसको डालो, shim करो. Shim में भी 3 ऑप्शन है, 15 सेकेंड, 20 to 2 to 30 minutes and 41 minutes. So shimming one time is okay. You can perform any of the nuclei analysis. Let's go further. And if you look at this thing, this tells you the reality of the machine, resolution. अब कोई भी instrument अपना calibrated thing छुपा नहीं सकता. That comes in front of us. And this is the real screenshot of my machine, which is located in Mumbai, which is installed in Mumbai. I use that, and you can see line width 50% is 0.34. That's the best resolution you get in benchtop NMR in the market, I'll tell you. Then this is the main software. You have different protocols. First protocol is Proton. You can see the first one, Proton. They have a 3 set protocols, sub-protocols. Quick scan, standard scan, power scan, 10 second, 1 minute and 10 minutes. So suppose your molecule is small, not small, I mean to say yours is not diluted, not very diluted. So you can go for this system. So you will get for 10 minutes, 10 second result. If your solution is your sample is very diluted, then you can customize your settings for analysis with this variable 80, Proton plus, that is called Proton extended, where you can customize your number of scan, repetition time, acquisition time, pulse angle. Then comes COSY, JRES. I think everyone can see, you can read, right? This top portion here. COSY, JRES, T1, T2, reaction monitoring. These are the features which will come into Proton section. Then you have, once you are done with the analysis, okay, you are done with the analysis, how you will pick the peaks, the integration, everything can be done with Mastronova software, which will be with this instrument, and you can do it with the Mastronova. This is how M-Nova, some people call it M-Nova, some call it Mastronova. So I'll say M-Nova. This is how the software look like, and you can integrate, you can do lot of features it have and get the results printed. This is how COSY or headcord will look like in M-Nova. And some of the experiment, you can see COSY for ibuprofen, one scan, 256 steps and 9 minutes. 9 minutes. And on traditional NMR, it takes around 1 hour, 2 hours. Am I right, sir? Right? It takes a lot of time. And sometimes for carbon correlation, you have to keep it overnight. So here you save a lot of time. You can see JRS. JRS is for calculating the coupling constant. Then lidocaine, it is one of the pharmaceutical molecule. You can see the HMQC, HMBC, the two analysis. The spectra looks very clear. You can find out the correlation between carbon and hydrogen. This is benzaldehyde, substituted benzaldehyde, aspirin, thiacalates. Now, if we look at the application, apart from our synthetic chemistry, where you can use in the laboratory. Suppose you get a different project where you have to analyze something. So, fermentation monitoring. I think sugar chemistry, they have this fermentation. They need to ferment sometime and they have to find out the sugar concentration and everything. So you can monitor the fermentation reaction here with the spin salt. Then comes paramagnetic, very important. Organometallic chemistry is very important. You have an organic molecule which contains a metal ion. Okay, metal ion. And what happens when you put this sample for analysis, you get a messy or some peaks are absent in the spectra because of the effect of metal ion. So what this feature in spin salt does is, it will nullify the effect of metal ion and gives you the pure organic peak, organic atom peak. So you don't have to worry with the organometallic molecules when you do spectra, NMR spectroscopy. So this is the best feature. You can see if you look at this spectra, when you do it in the proton, just proton protocol, you get like this spectra without any these two small peaks. But when you do it with the paramagnetic feature, you get this nice spectra with two peaks on this. So that is the difference. And nanoparticles, I have already told you T1, T2 studies. Can you see this? When you are doing with proton, you get this much only. But when you do paramagnetic, you get all other peaks also which were interfered by the metal ion. Polysaccharide chain analysis, sugar chemistry people always struggle with the NMR spectroscopy because of the large molecule and water solubility. But with this you can find the coupling constant. Reaction monitoring for panic peaks are again for the physical chemistry. Essential oil, natural chemistry, I think natural products, some people do it, natural product, drug discovery, they use essential oil and extract essential oil from few herbs or shrubs. So there you can use NMR for analysis. Then sample preparation, 5 mm diameter into 7-inch length, and 10 mg is the least you can use for analysis. I have used 5 mg also, this is just document, but I'll tell you 5 mg can also be analyzed, so diluted sample can be analyzed. Maintenance again, सब ठीक है, science सब ठीक है, but पैसा is important. Okay, so maintenance में पैसा नहीं लगना चाहिए. So you just need dust-free environment. Acid, of course, anything, even human being can't stay in acid fumes environment. So you have to keep your instrument away from that. Then comes a vibration-free bench. हम लोग कोई भी instrument ऐसे हिला के ऐसे हाथ में लेके analysis नहीं करते. So vibration नहीं होना चाहिए. Requirement, very basic requirement, you need 20 to 25 degrees Celsius of room temperature. Nothing else you need for this. Humidity 20 to 80%. Very common power system. These are anywhere you can install it. Power consumption is 200 watt. I think it's less. It's equivalent or less than a big halogen bulb. So it doesn't take you much of the energy. You will not get a lot of power consumption. Now our presence where we are, ISR Mohali, Banaras Hindu University Varanasi, NIT Kurukshetra, Gujarat University Ahmedabad, Bengaluru University Bangalore, JNTU Hyderabad, Anna University Chennai, and one of the instruments is in LABINDIA in Mumbai, application support lab, where you can visit anytime. You can analyze samples. You can satisfy yourself that instrument, whatever Deepak Sharma said was true or not. You can visit us and satisfy yourself with the results. This is our some details of our lab in Mumbai. Thank you. You can scan this barcode for watching the video of Magnitex spin solver. Thank you very much. Any questions? Yes, sir.
This system, your example setup is like carbocycle or this type. What happens when you use recycling? For example, if we take the case of maybe insulin, where it's a very close distance, is there any technical data sheet there for those things?
You mean to say a bigger molecule, complex molecule,
Not
cyclic structure?
Cyclic structure with heteroatom.
With the
For example, quinoline or substituted quinoline type.
Yeah. So you get the peaks, but you can expand it in the MNOVA and you can see the perfection of the spectra.
No, what I was asking that in heterocyclic compounds, especially, for example, this quinoline or isoquinoline, this type of fused ring system, where the aromatic proton, though they are different, but they get very closely spaced.
Yes, in the aromatic
Yes.
region you get all peaks.
So many times even a conventional NMR, for example, generally 400 megahertz, this is the standard one. Many of the cases becomes a little hard to see the peak position or peak splitting if there is any associated to that. So is it possible to analyze to that level with this one?
Like you can do it. You have to give a little bit time with proper concentration of sample, and you will get proper the peaks. And I know it is. I have done quinoline or isoquinoline. They give messy peaks. Then you can prove by GRS, then carbon, POSI, and this thing. So you get a proper result. Sometimes some molecules doesn't come in proton properly. I have seen that. There's some if you have impurity, then you can't do anything. Then you have to get it.
No, I am not speaking about impurity. Let us consider that the sample is pure, absolutely pure. But the compound itself is having this type of fused ring heterocyclic components. Let us consider only one heteroatom is present, because two heteroatom or multiple heteroatom will naturally complicate the situation. Single heteroatom, which is common case in almost all organic chemistry laboratories.
That's why that feature of proton extended is given, that you can customize your different feature parameters for certain molecules. Like you can change the acquisition time, repetition time. So more the scans, it will give proper spectra, proper positioning, the separation. I believe.
Actually, what I wanted to know that suppose let us increase the acquisition time, but suppose the sample is there.
We can discuss on my laptop. I'll tell you
data is there.
Yeah. Thank you, sir.
You told that there is no need of deuterated solvent. How we can identify between if you are using solvent just like
Very good question. Very good question. Yeah, you have a feature where you can cancel the major solvent. Suppose you are doing online reaction monitoring and you are doing reaction in chloroform, right? So if you are doing monitoring, you will get a big hump of chloroform, right? So the proton in the chloroform. So you can go into the reaction monitoring. You can cancel the unwanted solvent, and you will get the reactant peak only.
if you are not doing the online reaction monitoring, if you are doing only sample analysis, then we have
Then what happens? You know your solvent will give the peak at certain points, right?
Yes.
So you have to maintain the concentration, the amount of sample and the solvent. Like 5 mg or like you have diluted it to 1 ml, then of course you will get a big peaks.
why we are saying non-deuterated solvent can be used, that is a mastery actually. It goes a higher level when you use this non-deuterated. Otherwise, the deuterated solvents are only recommended for proper spectra. Okay. Because of fast automatic lock, you can use non-deuterated solvents. That is the funda actually. कि non-deuterated क्यों use कर सकते हैं क्योंकि वो locking is just fast automatic lock.
Okay, sir, how much it will cost generally? That instrument, whatever you are talking about.
How much will it cost? Our sales sir is the sales manager is here. You can talk to him with the commerce part. And I am just taking
we can discuss later.
Because I wanted to know, as we are an organic chemist,
yes,
so we are interested in buying it. So
okay. You must be knowing
what configuration?
As you tell, whatever 42.5 you told megahertz.
42.5 proton, carbon, fluorine,
Yeah.
everything you need.
Yes, at least 3, 13C, NMR and AP. If it requires, Ghosh also will require.
So around 80 lakhs, 80 to 90.
If we invest double the amount, then we can get a 400 megahertz also.
Who told?
Yeah, it is cost around 3.5 crores.
Is it a double? 80 to 90.
Yeah,
okay.
Then you make 1.6 into 2, 4 times more.
That is good or what I am talking.
No.
There are other companies also like diesel.
Okay, when you buy something, for example, like McD or KFC, we see 180 में burger, but when you get a bill, you get 250, 240 ऐसा. What all they are? Taxes, different kind of taxes, and this all, whatever traditional or anything, when you buy, you get hell lot of taxes, and what you are saying 1.6 crores is the base price. You are not including taxes, which goes around 2.3, 2.4 crores.
No, it is not less than 2.7.
This 400 megahertz is like, but if you, it goes, sir.
400 megahertz, Stuttgar usually within
2 crores.
Standard consideration within.
Sir,
but if you,
Manipur University couldn't purchase it. They do have fund of 1.7 crores or something like that.
They wanted the automated sensor,
No, minimum version size.
and the main funda is post-consumable cost. Everyone is looking for that.
That is the major.
That is the main.
That is the major problem with.
Like I visited few universities, they have the 400 megahertz instrument, but they are not getting nitrogen helium because they are in a remote area. They don't have the facility to get the instrument, cryogens for uska use. Without that, it can't work.
So can we analyze some powder sample with this?
With sample?
Powder sample.
No. Powder.
Powder sample. Okay. You mean solid state NMR. Okay. The solid state NMR needs spinning. Spinning is very important. So you can't do it solid state spectra. Solid state NMR.
So one of the important aspects is that you can see any journal policies. If you want to publish NMR data, so it needs to be at least from more than 200 megahertz. So in that case, so what you are going to do?
I know, sir, but nowadays, what is happening? Like you have, you suppose your university have 400 megahertz machine, and all other departments like 10, 20 professors with each 5 students, 10 students. Like 50 people working 150 molecules and coming to that same machine, which is performing 50 analysis. What this can help you if you have personal machine of yours. Suppose you started a reaction, you want to see suppose AB reactant, you want to see how pure it is. You can use it immediately. Suppose an intermediate which is short-lived, which is unstable, you have to analyze very fast. You can use it. You can use it anywhere. Because most of the professors nowadays, institute professor, I have worked with the University of Hyderabad and University of Mumbai. What professors demanding for personal instrument because they are facing issues. Their work are getting delayed because of the waiting of the analysis. So there you can use, but by final submission you can use that. for fatafat, fast analysis results you can use it. I understand your because you need to have the specification mentioned on the submission. That is like for submissioning and all this is useful, but it is very routine purpose. It is very good.
For streaming purpose.
Very good.
So maximum that frequency you have shown it is 42.5. 40 is the maximum.
Yes.
Some other companies they also bring 83 megahertz also.
How many?
83 megahertz.
It must be 60. Even
What
Magnetic
will
has
be sensitivity? What sensitivity we are operating? It is parallel.
It's all like so resolution is very important. That is very important. Resolution नहीं है तो instrument कितना भी बड़ा होगा तो it is not.
Because one thing is that mainly magnetic and spin, they are the major competitor in these fields over resolution. And if I consider the this one frequency for spin is probably 60 something and Ghosh is much lower. How do you compare this?
Okay. The first thing which company you go? If you go through the specifications, I think ours resolution is less than 0.5 hertz, and if you look at them, they write less than 1 hertz, which can be 0.8, 0.9 or 1. Again, then you look at the sampling tubes. I'm not sure, but I read it is 200 mm capillary. Once it is broken, your probe is gone and you have to wait for an engineer which will come and you will have to wait, both them. 5 mm into 7 length, 7 inch length. It won't grow, it won't break, you won't be waiting for any probe problem. Then there are sensitivity issue. We have for 42.5 megahertz, we have 100 greater than 100:1, whereas they give, I think, around 20:1. I had read somewhere, and because there are a lot of instruments and I can't remember everything, but I'll give you the details. But there were some mentions of 20:1. So if you buy also, you will get a big broad piece. That is not acceptable.
Can you perform the reaction which requires higher temperature by online monitoring?
Right. Yeah, you can, because case of that you heating a reaction, but you have to maintain a distance, a length where your solution get under room temperature for analysis, like that flow cell. If your reaction mixture is like 100 degree, 120 degrees Celsius, and it is directly going to the NMR instrument, of course there is 20 to 25 degrees Celsius limit. So you can't just put it like that. So you have to revolve it around for a length, then it will cool down, and then it will go to instrument for analysis. So you can perform, high degree reactions, heating reactions analysis also.
Once it is going to decrease the temperature 25 degrees.
Once you decrease the temperature,
then it will go to the for that 120 or 130. That will take some time. Much more time. Means once we are heated 120 degree for the analysis we further we have.
Correct. Suppose you are going to perform a series of samples, right? Series of sample like 5 minutes, 10 minutes, 15 minutes. So suppose first 5 minutes में जो आपने पूरा procedure किया, you are going to repeat the same thing. Same thing for other analysis also. So it not going to affect your results.
सर ऐसा भी हो सकता है कि अगर हम बीच में रिएक्शन स्टॉप कर दिया तो वो जो कंपाउंड है वो डिकम्पोज हो सकता है. ये
stop आपने
means temperature decrease reaction stop means then the compound may be decomposed.
Maybe decomposed.
Yeah, it is possible.
So that depends how you are taking it. Suppose you can ये जो flow chemistry जो pipe है उसको length मत करो, उसको ऐसा इससे pass करो ताकि आपका temperature immediately कम हो जाए. You have accessories. We can give you the accessories for cooling down and everything. That will be additional accessory. But as far if I'm gonna do that reaction with the heating stuff, what I'll do, I'll take that pipe oil, I'll put in a water bath, like around 20, like 14-15 degrees Celsius fridge ka temperature of water. And once it is passing, it will come to room temperature. So आपका crystalline नहीं होगा अंदर tube. अगर if goes like 15 के नीचे and all, तो room temperature 18-19 तक it will cool down. So you don't have to worry. And there are some limits for every instrument. So ये भी तो instrument ही है, right?
So when it comes to Indian market,
It is already, I told you, like it is already installed. You can visit anytime.
when exactly, in which year?
It's already came. When it came, when it launched in India, it's like 3-4 years ago. Yeah, these are our prestigious customers.
And one more thing, sir.
Yes.
You are talking about online reaction monitoring. I want to do a reaction like butyllithium grignard reagent. Can we pass that reaction through your instrument without quenching anything? Because without workup, it's very harmful to run a sample through NMR. As we know that grignards, butyllithium, they are very much reactive. Can we pass through the samples?
Because you are not coming in contact with magnet anyhow.
But still it has to be quenched before taking into NMR. That's what
I know. Then certain reactions you can perform, like this messy reaction you can perform, but you can cancel the major solvent. But I believe you can do it, one, because that doesn't come into the contact with the magnet, and quenching, because the reaction is going back to your vessel, so there is no coming in contact with environment, because it's closed system. Did you understand? It's like a transparent tube which will go through a magnetic field, will come back to the reaction. So you don't have to worry about the decomposition or anything happening to the reaction. So it's like closed system. इधर से आया, इधर से गया वापस. So that's why we like this is introduced. This is possible. अगर if reaction is open, if it is coming in contact, like if your palladium reaction is there, and once it get dries, it catches fire. Immediately it catches fire. So you need to have the reaction condition for analysis, and it is a closed system, so you are not changing anything. And it is using a parastatic pump. So you just take sample, throw it back.
if this instrument has this many positive points, then why is it not that much popular compared to like Bruker, Gisel, who are handling 400 megahertz, 600 megahertz? Why is it not that much popular since it has came before 4-5 years?
Because we Indians accept things after long time. कुछ भी नया
This is fact.
स्वच्छ भारत अभियान कितना आ गया, फिर भी हमने accept
Probably
NMR instrument.
I'll differ here. Because though this every equipment, it is having their own advantages and disadvantages. If I am wrong, you just please rectify it, because I am not from the production line. I am from the user's perspective. This benchtop NMR and the conventional NMR, both of these are having their own advantages, their own disadvantages also. This particular NMR, it is good for monitoring purpose. Here, conventional NMR cannot compete with it. Similarly, for final workup, that is confirmation of a structure, especially for a complicated structure, that conventional NMR has no match like this, because if everything could have been done with 40 megahertz or 80 megahertz, then probably 400 megahertz or 600 megahertz NMR would have not been invented at all. So 400 megahertz NMR is having its own space where no other NMR can enter, means higher component. I was just discussing this one. For example, if we want to work with a structure, maybe natural product, most of the natural products, just for example, Taxol is a compound, quite complicated. And I hardly believe that this 40 megahertz, whatever be the feature with it, will be able to resolve all the features of a complicated structure like that. But again, so there 400 or higher resolution NMR is absolute great. Again, in this type of work, this particular, suppose I am doing some work, especially for all the organic chemists, we have to go for reaction optimization. So I need to know that yes, a reaction is occurring, how much. Generally, when we do TLC, we have to depend on the visual optical density that we see over the NMR spot. If the starting material spot is becoming little dimmer and product spot is becoming much more brighter, we feel that okay, our reaction is progressing in a particular direction. If we see that the starting material is fully nil or almost nil in the TLC spot, okay, the reaction is over. That is the way we generally move. Here it comes into operation that after every certain amount of time, I can really take the spectrum of the material. And from the NMR spectrum, we know that NMR is a quantitative method. So there I know the peak of my starting material, any specific peak will choose for the starting material. Our probable peak for the product that we are expecting, that peak we'll see because that will be a new peak, obviously. So comparing the, what is called the peak space in between, that means comparing the concentration or the space under that peak, the way that we consider, we can say that within this amount of time that much reaction has got progressed. Here benchtop NMR is required because every now and then, maybe after every 15 minutes or maybe every after 1 hour, I cannot take the sample out of the material and go to the next building where my NMR is housed, and at that point of time I may not get the time slot also. And for a full day 400 megahertz NMR or like that, it is not possible to book in at least in Northeast Indian institutions. At least I can say. Maybe in those institutions where 5-7 NMR equipments are there, there it may be possible.
Very
so,
selected in.
Very selected. So these are the two aspects. Now depending on our need, we have to choose whether we really need this one or not. So it is not only by the feature, we have to go by need also. Means not only by emotion, by actual real component, whatever is required.
Thank you very much, sir. But I'll complete my statement of acceptance. What happened, I've been to many seminars where we had kept and people used to inquire. So few people come and they don't know about what is benchtop. And if they come to know also, they say NMR 80 lakhs, kuch nahi kare. They don't even listen. Because we have that attitude. The expensive thing is best, right? Today, iPhone and Android giving both same thing, but still people go for 72,000 phone. Why? Just a name and a quality they think of, but it is nothing. 400 of course gives you for complicated structures very good peaks. It also depend how you do it. It need mastery. You need patience. You have to learn it with this also. And this is a myth. Bigger the magnet, it will be good spectra. It always depend for NMR instrument resolution and sensitivity. These two parameters are satisfying. The instrument is very good. Otherwise, you take a bigger magnet and still not giving a good resolution, then it is no use. So that I want to say. Sir added very good thing. And yeah, thank you. Any more question? Thank you very much for listening me, and thank you organizers for inviting me here, because I love hills, mountains, and simplicity. This city is very simple, very natural, very nice. I will purify my lungs for by tomorrow, I think. So I will go around and I will purify myself, because we live in Mumbai and we are just running all the time, every time. We are just a minute, if we lose 1 minute, we get delayed or we get late by 15-20 minutes. We all run on trains. So train went, we are late, and you get a late mark in office. So yeah, thank you. I'm so happy to visit Imphal. I don't know much of geography, and after coming here, I'll study a lot of geography today about Seven Sisters. And it's a beautiful place. I saw from flight, and it is having a lot of water bodies here.
Yeah, that lake is there.
Yeah, what is that?
Look up.
It have this some circle. I didn't understand. What is that? I was sleepy. I just saw where are we on moon or somewhere? And then बाजू में मेरा बैठा था कोई and I asked them. He doesn't know Hindi. जाने दे भाई मैं I'll see whatever I can do. So yeah, thank you very much for giving your time, and yeah, so I'm done with this. Thank you.
Thank you very much, sir, for your valuable suggestions and experience. And that's the end of the today. So we'll meet tomorrow 10 a.m. morning. We continue our session.